What if 3I Atlas turns out to be a black swan event, a cosmic accident that changes history forever? They said it was just another interstellar wanderer, a frozen relic from nowhere, drifting quietly past the sun, leaving nothing behind but data and dust. We've seen these visitors before. Oumuamua in 2017 tumbling and silent. 2I Borisov in 2019 behaving exactly as comets should. Predictable, quantifiable, safe. But then it didn't leave. It began to shed water like a fire hose not near the sun where frozen volatiles should vaporize, but at nearly 3 times the distance between Earth and our star. Out there, most comets are dormant, quiet, frozen solid. But 3I Atlas doesn't care about our models. Its speed shifted. Its chemistry defied every pattern we've cataloged in hundreds of comets. And the acceleration, the way outgassing should push it off course, the math simply doesn't work. That's when astronomers stopped using words like interesting and started whispering a term you usually hear in financial markets and epidemiology: black swan. Here's what should make your skin prickle. This object was discovered on July 1, 2025, by the Atlas Survey Telescope in Chile. It's traveling at 61 kilometers per second, 137,000 miles per hour, on a trajectory that proves it came from another star system. And today, right now, as you're hearing this, October 29, 2025, it's rounding the sun at its closest approach at perihelion and beginning its outbound journey into darkness. We have one chance to understand this object, one window of observation before it fades into the cosmic background forever. And the data we're gathering isn't making sense. It's making questions. Why is it shedding water at a distance where water should be frozen? Why is its chemistry so extreme, an 8-to-1 ratio of carbon dioxide to water when most comets show the opposite? Why is its trajectory aligned almost perfectly with our planetary disk when statistically it should have arrived from a random angle? And why, despite heavy outgassing, does it show weaker acceleration than the physics predicts? Tonight, over the next 2 hours, we're going to explore 8 scenarios, 8 ways that 3I Atlas could transform from curiosity into crisis. Some are grounded in orbital mechanics and observational astronomy. Others venture into territory that will make skeptics roll their eyes. But that's the point. A black swan event isn't supposed to be obvious. It's supposed to be invisible until the moment it changes everything. We'll examine orbital perturbations that could cascade decades from now. We'll consider fragmentation events that might seed future threats. We'll ask whether this comet could interact with the sun in ways we've never witnessed. We'll explore the possibility of artificial signals buried in noise. We'll look at atmospheric anomalies, disclosure cascades, psychological shockwaves, and even reality glitches, moments when the instrumentation itself might reveal cracks in our understanding. And here's the uncomfortable truth we must face from the beginning. We might already be inside the black swan event. We might be watching it unfold in real time, misinterpreting it as curiosity rather than catastrophe. Because that's how these events work. They only make sense in hindsight after the paradigm has shifted, after the rules have changed, after it's too late to prepare. So let's begin. Let's pull back the layers. Let's examine the data, the speculation, the fear, and the wonder. Let's ask the question nobody wants to ask out loud. What if 3I Atlas isn't just passing through? What if it's the beginning of something we can't yet name? Stay with me. Keep your mind open but critical. And remember, the universe has surprised us before. It will surprise us again. Before we dive into anomalies and speculation, we need to establish exactly what we're dealing with. We need the facts, the measurements, the confirmed observations. Because the only way to recognize something impossible is to first understand what's possible. On July 1, 2025, at the Atlas Survey Telescope in Rio Hurtado, Chile, observatory code W68, astronomers detected a faint object moving through the constellation Serpens Cauda near the border with Sagittarius. At apparent magnitude 18, barely visible even to powerful telescopes, this newly discovered object was entering the inner solar system at extraordinary speed. The initial designation was cryptic, A11PL3Z, just another data point in a database filled with asteroids, comets, and cosmic debris. But within hours, as the discovery observations were submitted to the International Astronomical Union's Minor Planet Center, something became clear. This object's trajectory was unusual, very unusual. Follow-up observations began immediately. Professional observatories and amateur astronomers across the globe turned their instruments toward this mysterious visitor. The Zwicky Transient Facility in California found pre-discovery images dating back to June 14th. Additional Atlas observations were uncovered going back to early June, and as the data accumulated, the truth became undeniable. This object wasn't orbiting the Sun, it was passing through. Its orbit is hyperbolic, meaning its eccentricity is greater than 1. In the language of celestial mechanics, this is the signature of an interstellar trajectory. This object originated beyond our solar system, beyond the Oort cloud, beyond the gravitational influence of our Sun. It came from another star. On July 2, 2025, the Minor Planet Center made it official. They designated it 3IO Atlas, the third interstellar object ever confirmed. The KI stands for interstellar. The 3 places it in a category with only 2 predecessors, 1I Oumuamua discovered in 2017 and 2I Borisov discovered in 2019. In all of recorded history, humanity has detected exactly 3 visitors from beyond our solar system. Let that sink in for a moment. 3. In all the centuries we've watched the sky, in all the decades of modern astronomy, we've confirmed only 3 objects that demonstrably came from the stars. 3I Atlas also received the designation C2025N1, identifying it as a non-periodic comet discovered in the first half of July 2025. By the time it was officially named, astronomers had collected 122 observations from 31 different observatories around the world. But what exactly is this object NASA's observations with the Hubble Space Telescope captured on July 21st, when the comet was 207 million miles from Earth, revealed a teardrop-shaped cocoon of dust streaming away from a solid, icy nucleus? Because Hubble was tracking the comet's motion, the stationary background stars appeared as streaks in the exposure, a reminder that we're watching something in motion, something transient. The size of 3I Atlas remains frustratingly uncertain, depending on assumptions about how reflective its surface is, its albedo, and its composition. The nucleus could be anywhere from 0.32 kilometers to 5.6 kilometers in diameter. That's a massive range of uncertainty. The most likely estimate suggests it's less than 1 kilometer across, perhaps as small as 440 meters. Imagine an icy mountain tumbling through space at incomprehensible speed. And what speed? When discovered, 3I Atlas was traveling at approximately 61 kilometers per second relative to the Sun. That's 137,000 miles per hour. At that velocity, you could travel from New York to Los Angeles in less than 1 minute. This is not the gentle drift of objects in stable orbits. This is something with momentum, with a trajectory carved by a previous star system now cutting through ours like a bullet through fog. Its path is remarkable for another reason: inclination. The ecliptic plane, the flat disk where Earth and most planets orbit, serves as a reference. Most interstellar objects arriving from random directions in 3-dimensional space should show random inclinations. But 3I Atlas came in at only about 5 degrees relative to the ecliptic. It's moving retrograde opposite to the planet's direction, but nearly aligned with our solar system's architecture. Statistically, this is unusual. The probability of such alignment by pure chance, approximately 0.2%. Not impossible. Not proof of anything, but unlikely. The object's journey through our solar system has been meticulously tracked. It was located 4.51 astronomical units from the Sun at discovery about 675 million kilometers, roughly the distance from the Sun to Jupiter. On October 3, 2025, it passed within 0.19 astronomical units of Mars. That's approximately 28 million kilometers, closer than many near-Earth asteroid encounters. On October 29th today, it reaches perihelion at 1.36 astronomical units from the Sun, roughly 203 million kilometers, positioning it between the orbits of Earth and Mars. In the coming weeks, it will pass within 0.65 astronomical units of Venus on November 3rd, and next March in 2026, it will sweep past Jupiter at a distance of 0.36 astronomical units before leaving our solar system forever. Does it pose any danger to Earth? Number. Its closest approach to our planet will be about 1.8 astronomical units, roughly 270 million kilometers, occurring on December 19, 2025. This is not a collision scenario. This is not a threat in the conventional sense. But here's what makes 3I Atlas scientifically extraordinary. It's active, very active. Early observations were unclear whether this was a comet or an asteroid. Some astronomers, including noted comet hunter Alan Hale, reported no cometary features initially. But on July 2nd, multiple telescopes, the Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope at Mauna Kea, all detected a marginal coma with a potential tail-like elongation about 3 arcseconds in length. This wasn't an asteroid. This was a comet shedding material, creating the characteristic hazy atmosphere that gives comets their name. Observations by David Jewett and Jane Liu using the Nordic Optical Telescope confirmed it was clearly active, with a diffuse appearance. The Instituto de Astrofísica de Canarias, using the 2-meter twin telescope at Teide Observatory, found the same thing. The comet's coma, that glowing cloud of gas and dust, had a reddish color, indicative of dust composition similar to 2I Borisov. As July progressed into August, studies showed the coma became redder, suggesting an evolving surface or changing composition as the comet's activity increased with solar heating. So here's what we know with certainty. 3I Atlas is an active comet from another star system smaller than a typical city, moving faster than anything in natural orbit around our Sun, aligned unusually with our planetary plane, and shedding material in ways that are both familiar and strange. It's a cosmic messenger, a postcard from shores we'll never visit. And the message it's delivering is written in chemistry and physics, in patterns of light and shadow that our instruments are struggling to decode. What we're about to explore are the parts of that message that don't make sense, the sentences that seem grammatically impossible, the words written in a language we don't fully understand, because while 3I Atlas behaves like a comet in many ways, in other ways it doesn't. And those discrepancies, those small, nagging impossibilities, are what keep astronomers awake at night, wondering if we're watching something unprecedented unfold. The question isn't whether 3I Atlas is interesting. The question is whether it's paradigm shifting. And we're about to find out. When you heat ice, it melts. When you heat a comet, it sublimates. The ice transforms directly from solid to gas, skipping the liquid phase. This is basic physics. This is understood. Solar radiation provides the heat. The closer a comet gets to the Sun, the more intense the radiation, the more vigorous the sublimation. Water ice, the dominant volatile in most comets, begins significant outgassing when the comet reaches about 3 astronomical units from the Sun, roughly between Mars and Jupiter. Carbon dioxide dry ice sublimates, more easily becoming active further out, perhaps at 5 or 6 astronomical units. This is the playbook. This is what comets do. We've studied hundreds of them. We've built models. We've made predictions. And then 3I Atlas arrived and threw the playbook into question. Let me be clear about what NASA's James Webb Space Telescope discovered when it turned its infrared eyes toward this interstellar visitor. The coma, that hazy atmosphere surrounding the nucleus, is dominated by carbon dioxide, not water. Carbon dioxide, and the ratio is staggering, approximately 8 parts carbon dioxide to 1 part water. To put that in perspective, most solar system comets show ratios closer to 1 part carbon dioxide to 10 or 20 parts water. Water is usually the dominant volatile. Water creates the dramatic tails we see in images. Water is what makes comets spectacular. But 3I Atlas flips this relationship. In its coma, carbon dioxide is king by an enormous margin. In the entire history of cometary science, we've never observed a ratio this extreme, ever. The Webb telescope also detected water vapor carbon monoxide and carbonyl sulfide being released as the comet heats up. Observations by the Very Large Telescope in Chile found emissions of cyanide gas and atomic nickel vapor at concentrations similar to those seen in solar system comets. So it's not that 3I Atlas is entirely alien in composition. It shares chemical signatures with our local comets. But the proportions, the dominance of carbon dioxide, that's what's extraordinary. Here's why this matters. The composition of a comet tells us about the environment where it formed. Water ice condenses in relatively warmer regions of a protoplanetary disk. Carbon dioxide requires colder temperatures. If 3I Atlas is so rich in CO2 relative to water, it suggests the object formed in an exceptionally cold, carbon-rich region of its parent star system. Perhaps in the outer reaches far from the star where temperatures never rose high enough for water to be the dominant ice. This is speculation, but it's grounded in planetary formation theory. Different zones in protoplanetary disks have different temperature gradients, different chemical inventories. An object forming beyond what we'd call the snow line in another star system might naturally be carbon dioxide rich. But here's where it gets strange. 3I Atlas isn't just carbon dioxide rich, it's actively outgassing at a distance where most comets are dormant. At approximately 2.9 astronomical units from the Sun, still outside the orbit of Mars, this comet was already shedding water at rates typically seen much closer to the Sun. Imagine turning on a faucet in deep freeze and watching water pour out anyway. That's essentially what's happening here. The solar heating at 2.9 AU shouldn't be intense enough to drive such vigorous activity from a typical comet. Yet 3I Atlas formed a visible coma when it was outside Jupiter's orbit at a much greater distance than normal. Most comets have to get inside Jupiter's distance closer than 5 AU before solar radiation becomes intense enough to start the melting and outgassing that creates the characteristic tail. But this object was active earlier, brighter earlier, stranger earlier. Astrophysicist Jacqueline McCleary from Northeastern University explained it clearly. Carbon dioxide ice melts very easily compared to water ice. Dry ice sublimates at much lower temperatures than water ice. So if 3I Atlas is unusually rich in CO2, its early activity makes sense. The carbon dioxide starts outgassing while the water ice remains largely frozen. Only as the comet approaches perihelion does the water begin significant sublimation. This is a natural explanation. This is how science works. You observe something unusual, you propose a mechanism, you test it against other observations. And so far, the carbon dioxide hypothesis holds up. Tom Statler, NASA's lead scientist for solar system small bodies, has stated clearly that 3I Atlas behaves like a comet, that the evidence overwhelmingly points toward a natural body. Water outgassing confirmed. Dust production confirmed. Photometric behavior consistent with sublimation confirmed. All the hallmarks of a comet doing what comets do. But let's dig deeper into the dust. When sunlight scatters off the dust particles in a comet's coma, it becomes polarized. The electric field vectors align. The degree and angle of polarization depend on the size, shape, and composition of the dust grains. It's like a fingerprint. Astronomers observed 3I Atlas and found what they called extreme negative polarization. The polarization behavior doesn't match known solar system comets. The The phase angle dependence, the way polarization changes as the viewing angle shifts, is unusual, different, anomalous. Is this proof of something artificial? No, different dust composition, different grain sizes, different shapes. All of these could produce unusual polarization signatures. But it's another data point that doesn't quite fit the pattern we expected. Studies published in August 2025 measured how the comet's dust production scales. With distance from the sun, they used what's called a power law index, essentially a number that describes how sensitive the comet is to solar heating. For 3I Atlas, this index came out to approximately 3.8 plus or minus 0.3. That number means the comet reacts strongly to solar radiation. It's on the high end of known values. Changes in solar heating produce rapid changes in outgassing, and rapid changes in outgassing should produce rapid changes in acceleration, which brings us to the problem we'll explore in the next section. The dust production rate at 2 AU from the Sun, about 300 million kilometers, was measured at roughly 180 kilograms per second. Compare that to 2I Borisov, the previous interstellar comet, which was producing about 70 kilograms per second at the same distance. 3I Atlas is more than twice as active. Let me paint this picture for you. Imagine standing next to this cosmic iceberg as it races past the Sun. Every second, 180 kilograms of material dust. Ice particles, gas molecules erupts from the surface and streams away into space. That's like a fire hose of debris, continuous, powerful reshaping the nucleus with every passing moment. And yet for all this fury, for all this activity, something doesn't add up. The forces don't balance, the acceleration doesn't match. And that's where the real mystery begins. For now, let's acknowledge what's been established. 3I Atlas has extreme chemistry, unlike any comet we've studied. Its carbon dioxide dominance is unprecedented. Its early activity is unusual but potentially explainable. Its dust properties are strange but not impossible. These are anomalies, yes, but anomalies within the bounds of natural processes. Outliers, not impossibilities. The question is, do these anomalies cluster in a way that suggests something deeper? Or are we simply seeing the diversity of the cosmos, the natural variation that exists when you sample objects from thousands of different star systems formed under countless different conditions? For centuries, we've studied comets from one star system, ours. We've built theories based on a sample size of one stellar neighborhood. Now we're sampling star system number 2, number 3. Of course they're different. Of course they challenge our models. The universe is vast. The universe is diverse. And 3I Atlas might simply be showing us how narrow our perspective has been. Or it might be showing us that we've missed something fundamental. That our models aren't just incomplete, they're blind to entire categories of phenomena. The chemistry is strange, but stranger still is what happens when you try to calculate where all that outgassing should be pushing this object. Because the math breaks, the equations fail, and we're left with a comet that's defying Newton, defying Einstein, defying everything we thought we understood about how objects move through space. Let's examine that problem now. In the vacuum of space, motion is simple. An object in motion stays in motion unless acted upon by a force. For comets orbiting the sun, that force is gravity, the sun's immense mass pulling the comet along a curved trajectory. We can calculate this with exquisite precision. Newton gave us the equations. Einstein refined them. We can predict where a comet will be centuries from now, down to the kilometer. But comets aren't simple gravitational objects. They're active. They outgas. And when gas erupts from the surface, it acts like a tiny rocket engine pushing the comet slightly off its purely gravitational path. This is called non-gravitational acceleration, and it's predictable. Given a comet's distance from the sun, its size, its rotation rate, and its composition, we can calculate how much the outgassing should deflect its trajectory. This is well-established physics. We've done this successfully for hundreds of comets. Then 3I Atlas showed up and the calculations stopped working. Here's the problem stated as simply as possible. The amount of outgassing we observe should produce a certain level of non-gravitational acceleration. But the acceleration we actually measure is much weaker than predicted. The forces don't balance. The equation doesn't equal zero. Something is missing. Astrophysicist Avi Loeb, the same scientist who suggested Oumuamua might be an artificial light sail, has been vocal about this discrepancy. He's pointed out that 3I Atlas shows non-gravitational acceleration anomalies that don't fit standard models. Either the object is far more massive than size estimates suggest, or the outgassing isn't producing the expected thrust, or something else entirely is happening. Let me break this down. If the comet's nucleus is small, say 440 meters in diameter, on the low end of estimates, then the outgassing rates we observe are absurdly high. That much material erupting from such a small surface would require extraordinary activity pressures and temperatures that seem unrealistic. But if the nucleus is large, say 5.6 kilometers on the high end, then the lack of strong acceleration is absurd. That much mass should resist the outgassing jets to a degree, yes, but not this much. The jets should still impart measurable thrust. Either way, absurdity. Either the comet is too small for the activity we see or too large for the motion we measure. There's no comfortable middle ground where the numbers work cleanly. Loeb has suggested that if the jets are pushing against a very massive nucleus, the acceleration will naturally be small. Think of it like trying to push a boulder versus pushing a basketball. The same force produces vastly different results depending on mass. So perhaps 3I Atlas is denser than we think. Perhaps its nucleus isn't fluffy ice and dust like most comets, but something more compact. Rock, metal. Something with mass concentrated in a smaller volume. But that raises new questions. How would such a dense object form in the outer reaches of a planetary system where you'd expect fluffy, loosely bound ices? How would it survive billions of years of collisions and gravitational interactions without fragmenting dense bodies? Our survivors, yes, but they require specific formation conditions. Another possibility, the jets are symmetrical. Imagine outgassing erupting from multiple vents around the nucleus, all pushing in different directions. If the thrust vectors cancel each other out, the net acceleration would be small, even though individual jets are powerful. This is plausible. This happens. Or perhaps the nucleus is rotating in a specific way that distributes the thrust evenly over time. As the comet tumbles, different vents point in different directions, and over the course of a rotation period, the accelerations average out to near zero. Again, plausible. But here's what bothers researchers. We can't directly observe the nucleus. It's too small, too far away. We can't see the individual jets. We can't measure the rotation period with certainty. We can't map the surface to know where the active regions are located. We're inferring everything from the light reflected and the material ejected, and the inferences aren't converging on a coherent picture. Observations from the Nordic Optical Telescope measured the comet's brightness as it approached perihelion. They analyzed how brightness changes with distance using what's called the heliocentric distance exponent. This is the power law I mentioned earlier, a number that describes how sensitive a comet is to solar heating. For 3I Atlas, that exponent came out to 3.8 plus or minus 0.3. That indicates strong sensitivity to solar radiation. An exponent of 2 would suggest something driven by a highly volatile material like carbon dioxide, which we've confirmed is dominant. But 3.8 is higher. That suggests rapid, almost explosive responses to even small changes in solar heating. Yet the trajectory doesn't show corresponding rapid changes. It's as if the comet is reacting thermally, getting brighter, outgassing more without translating that energy into motion. The study also found that dust particles in the coma are unusually large. Not the microscopic grains you'd expect from a typical comet, but particles with an effective radius of about zero point 0.1 millimeters. That's huge by cometary standards, and large particles move slowly. They're ejected at roughly 5 meters per second, compared to typical ejection speeds of tens or hundreds of meters per second. Slow-moving dust responds sluggishly to solar radiation pressure. It takes time for these particles to be pushed away from the nucleus and form a tail. Early observations showed a sun-facing dust fan, not an anti-solar tail. Only later, as the comet got closer and the dust had time to accumulate and be swept back, did a traditional tail emerge. This explains some of the morphology we see, but it doesn't explain the acceleration problem. Large dust particles don't affect the nucleus's motion. They're already ejected material. The issue is what's pushing the nucleus itself. Another data point, the polarization I mentioned earlier. Extreme negative polarization, unusual phase, angle dependence. This could be telling us something about the dust grain properties, shape, composition, porosity. But polarization measurements are indirect. They depend on assumptions about scattering physics, about particle size distributions, about how light interacts with complex irregular shapes. What if our assumptions are wrong? What if interstellar dust behaves differently from solar system dust in ways we haven't characterized? What if the grains have coatings, or charge distributions, or internal structures that alter their optical properties? We're in territory now where every measurement requires an interpretation, and every interpretation depends on a model, and every model has assumptions. And when you stack assumptions on top of assumptions, uncertainty compounds. Here's where Avi Loeb's approach becomes interesting, even if controversial. He's proposed what he calls the Loeb scale, a quantitative framework for assessing whether an object might have technological origins. It's not about believing in aliens. It's about assigning probabilities to different hypotheses based on observed characteristics. For 3I Atlas, Loeb assigned a score of 4 out of 10 for possible technological origin. That's not high. It's not, this is probably artificial. It's, this has some unusual properties that warrant investigation. He cites 8 surprising qualities. Trajectory aligned within 5 degrees of the ecliptic probability. 0.2% displayed a sunward jet anti-tail in July-August. Not a typical optical illusion. Nucleus roughly 1,000,000 times more massive than Oumuamua, 1,000 times more than Borisov, yet moving faster. Arrival timing brought it close to Mars. Venus. Jupiter unobservable from Earth at perihelion probability 0.05% through 8. Additional observations regarding nickel to iron ratios and other chemical signatures. Now let me be absolutely clear, this is speculation. These probabilities depend heavily on assumptions about what typical interstellar objects should look like. But we've only confirmed 3. Sample size 3. You can't build robust statistics from 3 data points. However, Loeb's approach does something useful. It quantifies our uncertainty. It forces us to articulate why something seems unusual. And it reminds us that in science, we should investigate anomalies, not dismiss them simply because they seem unlikely. The mainstream response has been measured. Tom Statler and other NASA scientists emphasize that natural explanations remain far more probable than exotic hypotheses. Comets are weird. They're chaotic systems with complex surface activity. Every comet we study in detail surprises us in some way. But even the natural explanations require us to stretch our models. We have to invoke unusually dense nuclei or specific rotation states or dust populations with unexpected properties. We're still explaining the observations, yes, but we're doing so at the edges of parameter space. And that's where black swans live, at the edges, in the tails of the distribution, where probabilities are low but consequences are high. So here's where we stand. 3I Atlas is exhibiting non-gravitational acceleration that's weaker than its outgassing would predict. This could mean the nucleus is very massive, or the jets are symmetrical, or the rotation is finely balanced, or the dust properties are unusual, or some combination of all these factors. Or it could mean something else, something we haven't considered, something that requires new physics or new categories of objects. The math breaks. And when math breaks, you have three options. Check your arithmetic, revise your assumptions, or admit that reality is more complex than your equations capture. We've checked the arithmetic, we're revising the assumptions, but if both of those fail, we're left with the third option: the universe is trying to teach us something, and we're not listening carefully enough. The acceleration problem is the crack in the foundation. It's the thread that, when pulled, might unravel everything we think we know about these cosmic visitors. But to understand whether this is a crisis or just a curiosity, we need to first define what a crisis would even look like. We need to establish what a black swan event in space would mean, and that's where we're going next. The term black swan comes from the ancient assumption that all swans were white. For centuries, this seemed self-evident. Every swan observed in Europe was white. Natural philosophy suggested swans were white by nature, by definition. The idea of a black swan was used rhetorically to describe something impossible, something that couldn't exist. Then European explorers reached Australia and discovered swans that were indeed black. The impossible was real. The assumption was shattered, and suddenly every other assumption became questionable. If swans could be black, what else could defy expectation? The modern use of the term comes from philosopher and statistician Nassim Nicholas Taleb, who wrote extensively about rare, high-impact events that seem obvious in retrospect but were invisible beforehand. He defined black swan events with three characteristics. First, they lie outside the realm of regular expectations. Nothing in the past convincingly points to their possibility. They're not just unlikely, they're unthinkable until they occur. Second, they carry extreme impact. They don't just change a company or an industry, they shift entire paradigms. They rewrite the rules. They make the past look naive. Third, despite being unpredictable beforehand, human nature compels us to invent explanations afterward. We retrofit causality. We identify precursor signals. We say, of course, and we should have seen it, even though we didn't and couldn't have. The classic example Taleb used was the 2008 financial crisis. Experts assured everyone the system was stable. Risk was diversified. Mathematical models guaranteed that catastrophic collapse was statistically impossible, and then it happened. And afterward, everyone could point to warning signs: housing bubbles, over-leveraged banks, complex derivatives. But before the crisis, those warning signs were dismissed as noise, as ordinary volatility, as problems that smart people would manage. Black swan events are characterized by their retrospective predictability and prospective implausibility. They make sense looking backward. They're inconceivable looking forward. So how do we translate this into astronomy? What would constitute a black swan event in space? Let me propose a working framework. A space black swan must exhibit at least three of the following characteristics. First, unpredictability, beyond current models. Not just rare or unusual, but genuinely outside the parameter space of existing theories. An event that makes our best physicists say, "Wait, that shouldn't be possible." Second, high potential impact. This could manifest in several ways: direct threat to planetary safety, fundamental challenge to scientific understanding, disruption of observation and detection systems, or profound shift in human perception of our place in the universe. The impact doesn't have to be physical. It can be intellectual, cultural, philosophical. Third, irreversible consequences. Orbit shifts that persist for millennia, loss of data integrity that can't be recovered, new understanding that invalidates old textbooks permanently. Once a black swan lands, the world is different and you can't go back. Fourth, evidence of intentionality or physics. Anomalies beyond natural randomness. a signal that can't be explained by known astrophysical processes, a trajectory correction that defies inertia, a timing coincidence too precise to dismiss as statistical accident. Now let's apply these criteria to 3i Atlas in its current state. Unpredictability beyond current models. Partially. Its behavior doesn't perfectly match models, but it's not completely inexplicable. We can propose natural mechanisms, unusual composition, specific rotation states, dense nucleus. It's at the edge of parameter space, yes, but not obviously beyond it. High potential impact. Scientifically, absolutely. It's challenging assumptions about interstellar object populations, cometary chemistry and accretion conditions in other star systems. But practically directly, it's not threatening Earth. It's not on a collision course. The immediate impact is intellectual, not existential. Irreversible consequences not yet detectable. Its gravitational perturbations on other objects are being studied, but no confirmed cascade effects have been identified. It hasn't broken any equipment, hasn't forced us to rewrite textbooks. Not yet. Evidence of intentionality or physics anomalies. This is where things get murky. The acceleration discrepancy could be anomalous physics, or it could be natural complexity. We haven't fully modeled. The trajectory alignment could be intentional, or it could be a 0.2% coincidence that happened this time. No confirmed signals, no detected maneuvers. By these criteria, 3i Atlas is not currently a black swan event. It's interesting, it's anomalous, it's challenging, but it hasn't crossed the threshold into paradigm shifting. However, and this is crucial, black swan events are often recognized only in hindsight. You don't know you're in one until it's already happened. The financial system looked stable until it collapsed. The housing market looked sustainable until it burst. The unthinkable becomes thinkable only after it occurs. So the question isn't, is 3i Atlas a black swan? The question is, could it become one? And if so, through what mechanism, what specific sequence of events would transform this curious interstellar visitor into something that rewrites the rules? That's what the scenario analysis is for. We need to examine the pathways, the possible futures that branch from this moment. Some pathways lead to mundane outcomes. The comet fades, we learn interesting chemistry. Science advances incrementally. Other pathways lead to revelation. We discover something that forces us to reconsider fundamental assumptions. And a few pathways, low probability but high consequence, lead to genuine black swans events, so unexpected, so impactful that the world after is fundamentally different from the world before. Let me outline the 8 scenarios we're going to explore. Scenario 1, orbital domino. A small gravitational perturbation cascades over decades, eventually shifting another object's orbit into a collision course we didn't foresee. Impact, delayed, subtle, potentially catastrophic. Scenario 2, fragmentation event. The comet breaks apart, and one fragment shows anomalous behavior. Directed motion, unusual trajectory properties, suggesting internal structure or propulsion. Impact, immediate scientific crisis, possible evidence of artificial components. Scenario 3, solar disruption. An unusually powerful coronal mass ejection or solar flare coincides with perihelion passage in a way that seems too precisely timed. Impact infrastructure damage raised questions about comet-sun interactions we don't understand. Scenario 4, artificial signal. A brief radio pulse or structured emission is detected too weak to confirm, too structured to dismiss, buried in noise until someone runs the right algorithm. Impact, potential confirmation of extraterrestrial technology, destabilizing to society and science alike. Scenario 5, atmospheric anomaly. Earth's ionosphere or Mars's atmosphere shows transient disturbances correlated with the comet's passage, GPS delays, auroral activity, ionization spikes. Impact reveals previously unknown particle interaction mechanisms, possible near miss with something we didn't detect. Scenario 6, disclosure cascade. Coordinated but subtle release of information from space agencies, archival anomalies, resurfaced timing that suggests preparation for something larger, impact erosion of trust, conspiracy fuel possible, precursor to major announcement. Scenario 7, psychological singularity. Mass attention creates social consequences independent of the object's actual properties. Belief drives policy funding and research priorities. Impact, self-fulfilling prophecy. Societal shift based on perception rather than data. Scenario 8, reality glitch. Multiple independent timing systems show microsecond-scale anomalies during perihelion pulsar timing residuals, atomic clock drift spacecraft telemetry delays, all correlated, all inexplicable. Impact challenge to fundamental understanding of time measurement and space-time structure. These scenarios vary wildly in plausibility. Some are grounded in established physics, others are borderline metaphysical, but each represents a different flavor of surprise, a different path from curiosity to crisis. And here's the critical insight from Black Swan theory. You cannot assess the probability of these scenarios simply by looking at historical precedent. By definition, Black Swan events have no precedent. They're the things that haven't happened before. So probability estimates based on past observations systematically underestimate their likelihood. Taleb calls this the turkey problem. A turkey is fed every day for 1,000 days. From the turkey's perspective, each feeding confirms the hypothesis that humans are benevolent providers. The probability of being fed tomorrow based on past evidence approaches 100%. And then Thanksgiving arrives. The turkey's model built on 1,000 data points was catastrophically wrong because it couldn't account for the discontinuity. We're like turkeys observing the cosmos. We've watched the sky for centuries and seen certain patterns. We've built models, we've made predictions, and those models work beautifully until they encounter something outside their training set. An interstellar visitor that doesn't quite fit, an acceleration that doesn't quite match, a chemistry that's almost but not entirely wrong. These small wrongnesses might be noise, or they might be the first indications of something larger, something our models weren't built to see. The purpose of exploring these 8 scenarios isn't to predict which will happen. It's to prepare our thinking for the possibility that something will happen, to expand the space of what we consider possible so that when the improbable occurs, we recognize it quickly instead of dismissing it as error. Because in a universe of trillions of stars with billions of planetary systems, where physics operates on scales from quantum to cosmic, the strangest thing would be if everything were predictable. The strangest thing would be if we'd already seen it all. 3i Atlas might be ordinary, but it might not be, and the only way to know is to look carefully and honestly at what makes it extraordinary. Let's examine those scenarios now one by one, starting with the most scientifically grounded and moving toward the most speculative. And as we do, ask yourself, which of these would I dismiss as impossible and why? Because impossible is a word that comets from other star systems should make us use more carefully. The universe has surprised us before. It will surprise us again. The question is whether we'll be ready. Imagine dominoes arranged on a table. You flick the first one with your finger, a tiny amount of energy, a fraction of a joule. That domino tips and strikes the second, which strikes the third. And within seconds, a cascade has propagated across the entire table. The final domino falls, and you realize all of this motion, all of this energy transfer began with one small push. Now imagine the same principle, but instead of dominoes on a table, you have asteroids in space. Instead of seconds, the cascade takes decades. Instead of finger flicks, you have gravitational interactions. And instead of a final domino falling harmlessly onto wood, you have a multi-ton rock on a collision course with Earth. This is the orbital domino scenario. and it's the most scientifically plausible way that 3i Atlas could become a genuine black swan event. Let's establish the physics first. Every object with mass exerts a gravitational force on every other object. Newton told us this. Einstein refined the mathematics. This force decreases with the square of the distance, but it never reaches zero. No matter how far apart two objects are, they're still pulling on each other, however slightly. When 3i Atlas passed within 0.19 astronomical units of Mars on October 3, 2025, it was close enough that its gravitational field could tug on nearby objects. Now 0.19 AU is still about 28 million kilometers, roughly 75 times the distance between Earth and the Moon. That sounds far, but in gravitational terms, for objects in already complex orbits, this is close enough to matter. Mars has two small moons, Phobos and Deimos. Phobos orbits just 6,000 kilometers above Mars's surface, completing a circuit every 7.6 hours. Its orbit is already unstable on geological timescales. Tidal forces are slowly dragging it inward, and in about 50 million years it will either crash into Mars or break apart into a ring system. Deimos orbits farther out at about 23,000 kilometers and is much more stable. But stable is relative. Both moons are small, their orbits are maintained by a delicate balance of forces, and any significant perturbation could alter their trajectories. Did 3i Atlas perturb Phobos or Deimos? Almost certainly, at least infinitesimally. The gravitational influence of a mountain-sized object passing 28 million kilometers away is tiny but non-zero. The velocity change might be measured in millimeters per second, maybe less. That's nothing. That's negligible. Except orbits are chaotic systems. They're sensitive to initial conditions. A change in velocity of 1 millimeter per second doesn't matter today, but over hundreds of orbits over years, that change compounds. The moon's position in its orbit shifts. What was once a circular path becomes slightly elliptical. The periapse, the closest point to Mars, gradually lowers, or raises, or shifts in inclination. Fast forward 30 years. That millimeter per second perturbation has become a kilometer difference in position. The moon is no longer where you thought it would be. If there's a spacecraft orbiting Mars, if there are trajectories planned that assumed the moon's location based on old models, those trajectories are now slightly wrong. Now Phobos and Deimos crashing into spacecraft is a small concern. We track them carefully, we update our models, but consider what else. Mars has co-orbital asteroids, Trojans, objects that share Mars's orbit trapped at the L4 and L5 Lagrange, points, stable gravitational pockets 60 degrees ahead of and behind Mars. These Trojan asteroids are gravitationally shepherded by Mars. They orbit in a quasi-stable dance held in place by the balance between the Sun's gravity and Mars's influence. But that stability is contingent. It depends on the Trojans maintaining specific velocities and positions. If you nudge one of them, if you change its velocity by even a few meters per second, it might drift out of the Lagrange point. And once it's out, its orbit is no longer stable. It's no longer trapped. It becomes a free-flying object whose trajectory depends on the gravitational influences of Mars, Jupiter, and the Sun. And those influences are chaotic. Let's construct a hypothetical scenario grounded in real orbital mechanics. Suppose 3i Atlas passed near, not colliding with, just near a Mars-Trojan asteroid. This asteroid has a mass of maybe 1 billion kilograms. The comet has a mass perhaps 10,000 times larger, 10^14 kilograms, if the nucleus is on the larger end of estimates. The gravitational interaction is brief, lasting just hours as the comet sweeps past, but it's enough to change the asteroid's velocity by, let's say, 5 meters per second. That's walking speed, trivial in the moment. The asteroid begins drifting. Its orbit isn't perfectly Martian anymore. Instead of circling at a constant 1.52 AU from the Sun, its trajectory becomes elliptical. The perihelion, the closest point to the Sun, drops to 1.4 AU. The aphelion, the farthest point, rises to 1.6 AU. Now the asteroid crosses a different orbital space. And in that space there are other objects. Maybe it crosses the orbit of a near-Earth asteroid, another small body that already has an orbit bringing it close to Earth's vicinity. The two objects don't collide, but they pass close enough that their mutual gravitational interaction perturbs both orbits. The near-Earth asteroid's orbit shifts slightly. Its perihelion drops from 1.0 AU to 0.98 AU. That brings it closer to Earth. Not on a collision course yet, but closer. 10 years pass, 20 years. The asteroid completes multiple orbits, and each time it passes near Earth, gravitational interactions tweak its trajectory. These tweaks are small but cumulative. After 30 years, the asteroid's orbit has evolved significantly. What was once a close approach of 0.02 AU, about 3 million kilometers safe, is now a close approach of 0.001 AU. That's 150,000 kilometers, closer than the Moon. And we never connected it back to 3I Atlas because the causal chain is too long, because the perturbation happened 30 years ago and involved multiple intermediate objects and occurred at Mars, not Earth. This is the orbital domino scenario. It's not about direct collision. It's about cascading consequences across decades, where small changes compound into large effects, and the triggering event is invisible or forgotten. How plausible is this? Let's assess honestly. Gravitational perturbations are real. They happen constantly. Every planet tugs on every asteroid. Jupiter, with its enormous mass, regularly perturbs objects and ejects them from the solar system or sends them careening inward. Mars is much smaller, but its Trojans and nearby asteroids are sensitive to outside influences. Chaotic orbital mechanics are real. Small uncertainties in position and velocity grow exponentially over time. After a certain number of orbits, predictability breaks down. This is why we can't calculate the exact position of asteroids centuries from now. The errors compound faster than we can refine the measurements. Near-Earth asteroids are real. We track thousands of them. We know many more exist that we haven't detected yet. Some have orbits that bring them close to Earth regularly, and some of those orbits are not fully characterized because we lack sufficient observations. So yes, this scenario is plausible. The physics is sound. The mechanisms are understood. What's uncertain is the probability. Did 3I Atlas actually perturb something significant? Are there objects whose orbits were altered enough to matter? We don't know. We don't have complete orbital data for every small body in the solar system. We don't have the computational resources to model every possible interaction. And we don't have telescopic coverage to detect subtle changes in trajectories for objects that are already faint and hard to track. The gaps in our knowledge are vast, and those gaps are where risks hide. Here's what makes this scenario a potential black swan. The consequences are delayed. By the time we recognize the problem, by the time an asteroid is on a confirmed collision course, the perturbation that set it in motion is ancient history. We'd have no way to trace it back. We'd just see another asteroid, another threat, another object requiring deflection or evacuation planning. And we'd never know it was caused by an interstellar visitor we watched with fascination, but didn't fully understand in October 2025. This is why planetary defense is difficult. It's not enough to track asteroids as they are today. You need to model how their orbits will evolve over decades, accounting for every significant gravitational influence. You need to track not just the known threats, but the potential threats, the objects whose orbits might shift into dangerous configurations given the right perturbations. And you need to account for interstellar visitors. Because if they're common, if one arrives every few years, then each one is a potential domino flick, a potential initiator of cascades we won't see until it's too late. Should we be worried specifically about 3I Atlas? Probably not. The probability of it having perturbed something into a future collision is low, but low is not zero. And over time, over many interstellar visitors, the cumulative probability rises. The verdict orbital domino is plausible, significant, and invisible in the short term. It's a legitimate black swan pathway, not because it's likely, but because if it happens, we won't recognize the causality until decades after the triggering event. And by then, the dominoes will have already fallen. Comets are fragile. They're not solid monoliths of ice and rock. They're loosely bound aggregates, held together more by gentle gravitational self-attraction than by structural strength. Imagine a pile of gravel loosely frozen together with dirty ice tumbling through space. That's a comet. And because they're fragile, they break. All the time. Thermal stress is the usual culprit. As a comet approaches the sun, one side heats up while the other remains cold. This temperature gradient creates mechanical stress. Ice sublimates unevenly, creating pressure differentials. Cracks form, material sloughs off, and sometimes the entire nucleus fractures into multiple pieces. We've witnessed this repeatedly. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before slamming into Jupiter in 1994, each fragment creating spectacular impact plumes in the Jovian atmosphere. Comet Schwarzmann-Wachmann 3 has fragmented multiple times over decades, shedding pieces with each pass near the Sun. Comet Ison disintegrated entirely during its perihelion passage in 2013, evaporating into a cloud of dust that dissipated within days. Fragmentation is normal, it's expected. It's one of the most common things comets do. So the question isn't whether 3I Atlas might fragment. The question is, if it does fragment, will the pieces behave normally, or will something break in a way that defies explanation? Let's establish what normal fragmentation looks like. When a comet breaks apart, the fragments inherit the parent body's velocity. They're all moving in roughly the same direction at roughly the same speed. But they also receive additional velocity from the breakup event itself and ejection velocity. This ejection velocity depends on the mechanism of fragmentation. If the nucleus simply cracks due to thermal stress, the fragments drift apart slowly, maybe a few meters per second. If there's internal pressure from sublimating ice, imagine a pocket of gas exploding beneath the surface. The ejection velocity can be higher, tens of meters per second. Crucially, the ejection velocity is dictated by physics, by conservation of momentum, by the energy available from thermal and mechanical processes. We can calculate what the fragments' trajectories should look like. We can predict their brightness evolution, their subsequent outgassing, their long-term behavior. But what if a fragment doesn't match those predictions? Imagine this. 3I Atlas is outgassing heavily as it rounds perihelion. Jets are firing from its nucleus, creating thrust. The asymmetric outgassing causes rotation tumbling, increasing mechanical stress. And then during perihelion, or shortly after the nucleus fractures, a significant piece breaks away, call it fragment A. Telescopes detect fragment A as a new, faint point of light near the primary nucleus. Initial observations show it's moving away from the parent body, which is expected. But as astronomers track it over the following days, something strange becomes apparent. Fragment A is decelerating relative to the outgassing direction. That shouldn't happen. If the fragment was ejected by outgassing jets, it should be moving away from the nucleus in the direction those jets were pushing. And it should be moving at a constant velocity or even accelerating slightly if it has its own outgassing. But instead, it's slowing down, as if something is pulling it back, or as if there's some internal mechanism reducing its velocity. The numbers don't work. The trajectory doesn't match ejection physics. Astronomers would first assume measurement error. They'd refine the observations, gather more data, check calibrations. But suppose the deceleration persists. Suppose multiple telescopes using different instruments and different techniques all confirm the same thing: fragment A is not behaving like a passive chunk of ice and rock. Then the hypotheses begin. Maybe the fragment has internal cavities that channel outgassing in a specific direction, creating thrust, opposing its motion. Plausible. But you'd need a very specific internal structure, almost engineered, to produce sustained thrust in exactly the right direction to cause deceleration. Maybe the fragment is tumbling in a way that creates asymmetric outgassing, and over time this averages to a net deceleration. Possible, but again, it would require a very specific combination of rotation state active regions and mass distribution. Or maybe, and this is where we enter speculative territory, maybe there's something inside the fragment, not ice, not rock, something directing the motion, something responding to the environment in a way that produces non-random thrust. I'm not saying this is likely. I'm not claiming 3i Atlas will fragment into artificial components. I'm exploring what it would mean if a fragment showed behavior that couldn't be explained by standard cometary physics. It would mean one of three things. First possibility. Our understanding of cometary fragmentation is incomplete. There are natural processes we haven't characterized that can produce directed motion. We need better models, more observations, refined physics. Second possibility. The fragment has unusual internal structure possibly created by unique formation conditions in its parent star system. It's natural but exotic, a statistical outlier formed under circumstances we've never observed. Third possibility. The fragment contains something artificial, a probe, a sensor, a piece of technology embedded in or attached to the comet, now exposed by the fragmentation event. The third possibility sounds like science fiction, and it probably is. But let's examine it seriously for a moment, because this is exactly the kind of scenario that would constitute a black swan. Suppose a civilization wanted to study other star systems. Suppose they didn't have faster-than-light travel, so they couldn't send crewed missions. But they could send probes, small, durable instruments designed to survive for billions of years in the cold of interstellar space. How would you design such a probe? You might embed it in a comet or asteroid. The ice provides shielding from radiation. The object's natural trajectory carries it between star systems without requiring fuel, and when it approaches a star, the solar heating might trigger activation. Wake the probe from hibernation. Begin data collection, maybe even deploy instruments. During perihelion, thermal stress might cause the comet to fragment, exposing the probe. And if the probe had any remaining propulsion capability, even small attitude thrusters or directed gas jets, it might exhibit motion that doesn't match natural fragment behavior. This is wild speculation, but it's not physically impossible. And it's exactly the kind of hypothesis that planetary defense and SETI researchers should consider when studying interstellar objects, not because it's probable, but because the consequences of missing it would be profound. Avi Loeb has made similar arguments about Oumuamua, suggesting its unusual acceleration could be consistent with a thin light sail rather than a natural object. The mainstream response was skeptical, and rightly so. Extraordinary claims require extraordinary evidence. But Loeb's point was procedural. We should look. We should gather data sufficient to rule out exotic explanations, not simply assume they're false because they seem unlikely. For 3i Atlas, the fragmentation scenario offers a testable prediction. If the comet fragments, and if any fragment shows anomalous motion, we can observe it closely. We can measure its trajectory with high precision. We can analyze its spectrum to determine composition. We can use radar to probe its structure. We can point radio telescopes at it to check for emissions. And if all of that yields ambiguous results, if the motion remains unexplained, if there are hints of structure or material inconsistent with natural composition, then we'd have a genuine mystery. Not proof of anything, but a mystery worth investigating extensively. As of perihelion. On October 29, 2025, there are no confirmed reports of fragmentation. But comets often fragment during or shortly after perihelion when thermal stress is highest. Follow-up observations over the coming weeks are critical. If brightness suddenly increases, if multiple components appear in high-resolution images, if the trajectory shows unexpected deviations, those would be signs. And here's the challenge. If a fragment did show anomalous behavior, every day would matter. Every day, the fragment fades as it moves away from the sun and Earth. Every day, it becomes harder to observe. Eventually, it disappears into the darkness, and we're left with fragmentary data, pun intended, incomplete measurements, unanswered questions. We'd be haunted by what we might have missed. And decades later, when another interstellar object arrives, we'd wonder, should we have looked harder at Fragment A? Should we have sent a spacecraft? Should we have taken the anomaly more seriously? The verdict: fragmentation with anomalous behavior is possible, potentially paradigm-shifting and time-sensitive. It's a scenario that requires vigilance, rapid response, and willingness to investigate even unlikely possibilities. Because if just one fragment of one interstellar comet turns out to be something other than ice and rock, the implications cascade far beyond astronomy. They touch every assumption we have about our place in the universe, about whether we're alone, about whether the cosmos is populated by civilizations that send messages across the stars embedded in comets. And if we miss it, if we dismiss the anomaly as measurement error or natural complexity, we might never get another chance. The fragments of 3I Atlas, if they exist, are temporary visitors. They'll fade and vanish. The question is, will we be watching closely enough when they do? Now we venture into territory where probabilities drop, but stakes rise dramatically. We're moving from scenarios grounded in gravitational mechanics to scenarios requiring coincidence, correlation, or physics we don't fully understand. These are the possibilities that make scientists uncomfortable, not because they're impossible, but because they challenge the boundaries between observation and interpretation. Let's start with solar disruption. The sun is not the stable, unchanging orb it appears to be in our daily experience. Its surface roils with convection plasma churning at temperatures of millions of degrees. Its magnetic field twists and tangles, forming loops and filaments that extend hundreds of thousands of kilometers into space. And periodically, explosively, this magnetic energy releases. Coronal mass ejections, CMEs, are massive bursts of plasma and magnetic field hurled from the sun's corona into space. A single CME can carry billions of tons of solar material traveling at speeds up to 3,000 kilometers per second. When these ejections are aimed at Earth, they can compress our magnetosphere, trigger spectacular auroras, and in extreme cases induce currents in power grids strong enough to damage transformers and cause widespread blackouts. Solar flares are even more energetic, sudden brightenings in the sun's atmosphere releasing energy equivalent to billions of nuclear bombs. They emit radiation across the electromagnetic spectrum from radio waves to X-rays and gamma rays. The largest flares can disrupt radio communications, damage satellites, and pose radiation hazards to astronauts. The sun operates on an 11-year cycle with periods of maximum activity, solar maximum featuring frequent CMEs and flares, and periods of quiet solar minimum with relatively few events. But even during quiet times, the sun can surprise us. Prediction of specific events remains difficult. We can forecast general trends, but we can't say with certainty when and where the next major flare will erupt. So here's the question for our scenario. Could 3I Atlas passing through perihelion somehow trigger or coincide with significant solar activity? Mainstream astrophysics says no emphatically. The comet is tiny compared to the sun, even at closest approach, 1.36 AU, roughly 203 million kilometers. It's far enough that its gravitational influence on the sun is essentially zero. We're talking about a mountain-sized object trying to influence a star with 3,000 times the mass of Earth. It's like a mosquito trying to perturb an elephant. And magnetic effects. The comet's coma is ionized plasma, yes, but the sun's magnetic field is so vastly more powerful that the comet's contribution is negligible. It's like bringing a refrigerator magnet near an electromagnet the size of a building. The small magnet is irrelevant. But let's consider second-order effects. What about feedback mechanisms we don't understand? The sun's corona is a complex nonlinear system. Small perturbations can, under specific conditions, trigger large responses. This is the nature of chaotic systems' sensitivity to initial conditions. Could the ionized coma of 3I Atlas couple with the sun's magnetic field in an unexpected way? Could it act as a trigger for instabilities that were already building? Could it perturb the delicate balance of forces in an active region, tipping a system that was already near a tipping point? I'm not claiming this is likely. I'm exploring whether it's possible. And the honest answer is we don't know. Solar physics is extraordinarily complex. We have models, yes, but those models struggle to predict specific events. If we fully understood the mechanisms that trigger CMEs and flares, we'd be much better at forecasting them. Now let's check the observational record. Were there significant solar events around October 29, 2025? Did any major CMEs erupt during the perihelion window? Did solar activity spike in a way that correlates with 3I Atlas's closest approach? Based on the search results I accessed earlier, there don't appear to be reports of major solar disruptions coinciding with perihelion. No unusual CMEs aimed at Earth, no record-breaking flares. The scenario based on current data doesn't seem to have manifested. This weakens the solar disruption hypothesis significantly. Without a temporal correlation, without a solar event that occurred precisely when the comet was closest, we have no evidence to support the idea that the comet can trigger solar activity. However, the absence of an event this time doesn't mean the scenario is impossible for future interstellar visitors. It remains a valid question. Could there be comet-sun interactions we haven't characterized? Should we be monitoring solar activity closely whenever interstellar objects pass perihelion? The answer from a precautionary perspective is probably yes. The cost of watching as minimal solar observation happens continuously anyway, but the benefit of detecting an unexpected correlation could be substantial. If we ever did observe a major solar event coinciding with an interstellar object's perihelion, it would warrant serious investigation. For now, though, we move this scenario into the unlikely but worth monitoring category. It's not a black swan for 3I Atlas specifically, but it remains on the list of possibilities for the broader population of interstellar visitors we'll encounter in coming decades. Now let's turn to something even more speculative but potentially more profound: artificial signals. Since 1960, when Frank Drake pointed a radio telescope at nearby stars and listened for signals from extraterrestrial civilizations, humanity has been engaged in the search for extraterrestrial intelligence, SETI. For more than 6 decades, radio telescopes have scanned the sky searching for narrowband signals, structured emissions, anything that couldn't be produced by natural astrophysical processes. And we've found nothing definitive. The famous WOW signal, detected in 1977, remains unexplained but is never repeated. Fast radio bursts, initially mysterious, now appear to be natural phenomena, likely from magnetars. Every candidate signal either fades into noise or gets explained by natural sources. But SETI operates under specific assumptions. It assumes signals will be continuous or repeating. It assumes civilizations broadcasting to the galaxy would want to be heard, would transmit for long periods, would aim at promising star systems. It assumes communication as the primary goal. But what if you're not broadcasting? What if you're traveling? Consider a different scenario: an interstellar probe embedded in a comet, as we discussed in the fragmentation section. This probe has been dormant for billions of years, crossing the vast distances between stars. As it enters a planetary system, solar radiation warms it. Systems activate, instruments deploy, and maybe, just maybe, it transmits. A brief pulse, a status report back to its origin civilization, or a beacon to any technological civilization in the system announcing its presence. Would we detect such a signal? That depends on many factors. Duration. A pulse lasting only seconds would be easy to miss unless we were looking at exactly the right time in exactly the right direction. Strength. A weak signal just above the noise floor could be dismissed as interference. Frequency. If the signal falls outside the bands that SETI primarily monitors, it might not be captured at all, and here's the critical issue. Radio telescopes don't point at comets looking for signals. Why would they? Comets are natural objects. They're icy rocks that reflect light and scatter radio waves, but don't generate coherent emissions. We don't expect signals from them, so if 3i Atlas emitted a brief radio pulse during perihelion, say, at 1.42 GHz, the hydrogen line frequency that SETI considers a universal marker, would we have detected it? Maybe. All-sky radio monitors like CHIME in Canada or ASCAP in Australia continuously scan large patches of sky. If a pulse occurred, it might show up in their data. But those systems process enormous amounts of information every night, and they filter heavily to reduce false positives. A brief pulse coincident with the comet's position might be flagged as radio frequency interference, human-made terrestrial emissions that contaminate astronomical observations. Standard algorithms would filter it out automatically. The data would be logged but not analyzed. And unless someone specifically went back and looked for signals from the comet's position, the pulse would remain buried in archives. This is the challenge of searching for the unexpected. Our detection systems are optimized for specific categories of signals. Anything outside those categories gets classified as noise or error. And unless we specifically reanalyze data with new hypotheses in mind, we miss entire classes of phenomena. Avi Loeb has argued that we should be doing exactly this kind of retrospective analysis for interstellar objects. We should be checking radio archives for coincident emissions. We should be applying new algorithms, including machine learning systems that can identify structured patterns without being told what to look for. Has anyone done this for 3i Atlas publicly? No confirmed radio signals have been reported. But that doesn't mean no one has looked or that no one has found anything ambiguous. Radio astronomy generates sensitive data, and scientists are often cautious about announcing potential signals until they can be confirmed or explained. So let's engage in a thought experiment. Suppose a team of researchers analyzes archival radio data from October 2025. They apply a machine learning algorithm designed to detect non-random patterns, and they find something, a brief emission 3 seconds in duration from the direction of 3i Atlas during perihelion. The signal strength is just barely above noise. The frequency is in a band consistent with intelligent communication. The structure shows modulation. It's not a simple tone but has embedded complexity. What happens next? First, the team tries to rule out terrestrial interference. They check whether the signal could be from satellites, aircraft, ground-based transmitters. They compare it to known sources of RFI. If they can definitively identify it as terrestrial, they discard it. But suppose they can't. Suppose the signal characteristics don't match any known interference source. Then they face a decision. Do they announce it? Do they publish? This is where science becomes social and political. Announcing a potential extraterrestrial signal without absolute confirmation risks credibility. If you're wrong, your reputation suffers, your institution looks foolish. Funding agencies question your judgment, but not announcing carries its own risks. If the signal is real, if it's evidence of technology and you bury it, you're withholding potentially the most important discovery in human history. This dilemma is why SETI has protocols. The Post-Detection Task Force guidelines outline steps for verification, peer review, and responsible announcement. But those protocols assume repeatable signals, opportunities for confirmation. A brief pulse from a transient object doesn't fit the framework. So what would likely happen? The team would probably publish a cautious paper. They'd present the data honestly, noting the signal's existence but emphasizing the ambiguity. They'd say, "We detected an anomalous emission consistent with artificial origin, but we cannot rule out natural or terrestrial explanations. Further observations are needed." And then the object would be gone. Too far, too faint to follow up, and we'd be left with one data point insufficient for conclusions, enough to drive speculation, but not enough to prove anything. This is the artificial signal scenario. Not dramatic, not definitive, just ambiguous, frustrating, tantalizing. A hint of something that might be extraordinary or might be nothing, and no way to resolve the question. Is it a black swan? Potentially, yes. If the signal exists and if future analysis strengthens the case for its artificiality, it would force us to reconsider everything. Not just whether we're alone, but how we've been searching, what we've been missing, how many other signals might be buried in decades of archived data. But as of now, with no confirmed signals reported, this scenario remains speculative. It's a possibility worth investigating, but not an event that has occurred. The verdict, solar disruption, appears unlikely for 3I Atlas specifically, as no major solar events coincided with perihelion. Artificial signals remain unconfirmed, though archival analysis could reveal hidden patterns. Both scenarios remain relevant for future interstellar objects and highlight gaps in our monitoring and analysis capabilities. The question isn't just what 3I Atlas is telling us, it's what we're prepared to hear. Sometimes the most important signals aren't loud, they're whispers. Subtle disturbances in systems we monitor constantly, but rarely correlate with unexpected events. These are the anomalies that hide in noise margins, the deviations that fall just below significance thresholds, the patterns that only emerge when you look for them specifically. Let's explore two such scenarios: atmospheric anomalies and disclosure cascades. Both involve detection of effects so subtle they could easily be missed. Both require careful analysis of existing data, and both have the potential to reveal that 3I Atlas's influence extends beyond what we've recognized. First, atmospheric anomalies. Earth's atmosphere isn't a single uniform layer. It's stratified into regions with distinct properties. The troposphere, where weather occurs, extends up to about 12 kilometers. The stratosphere goes to 50 kilometers. The mesosphere to 85 kilometers. And above that, from 100 to 1,000 kilometers altitude, lies the ionosphere. The ionosphere is special. Solar ultraviolet radiation strips electrons from atoms, creating a plasma, a soup of charged particles. This plasma affects radio waves, reflecting certain frequencies and allowing long-distance communication. It also affects GPS signals, which must pass through the ionosphere to reach ground receivers. GPS works by precise timing. Satellites broadcast signals time-stamped by atomic clocks. Receivers on the ground detect those signals and calculate distance based on travel time. But ionized plasma delays the signals. The more electrons, the longer the delay. So GPS systems constantly measure ionospheric electron density and correct for it. The ionosphere is sensitive to solar activity. When a solar flare erupts, the burst of radiation ionizes more atoms, increasing electron density, creating disturbances that can disrupt GPS and radio communications. This is well understood. This is monitored continuously by space weather services worldwide. But the ionosphere is also sensitive to other things. Meteor showers, for instance. When Earth passes through a debris stream, thousands of meteors burn up in the upper atmosphere. The vaporized material creates transient layers of enhanced ionization. These layers can reflect radio waves in unusual ways, cause brief GPS signal degradations, create anomalies that last minutes or hours before dispersing. So here's the question: could 3I Atlas affect Earth's ionosphere? The comet passed closest to Earth at about 1.8 AU, roughly 270 million kilometers. That's far. Too far for direct physical interaction. The nucleus can't touch our atmosphere. But the coma extends far beyond the nucleus, and the ion tail, the stream of charged particles pushed away by solar wind, can stretch for millions or even tens of millions of kilometers. Could that tail have intersected Earth's magnetosphere? Could charged particles from the comet have been funneled down magnetic field lines toward the poles? Could they have created transient ionization, however brief? The geometry matters. We'd need to reconstruct the comet's position, its tail orientation relative to the solar wind, Earth's position, and magnetic field configuration. If all of those factors aligned in a specific way, if the ion tail happened to brush Earth's magnetosphere during a brief window, then yes, particles could have entered the ionosphere. Would we have noticed? That depends on whether anyone was looking and whether the effect was above detection thresholds. Ionospheric monitoring happens constantly. Ground-based receivers measure electron density. Satellites observe from above. But unless someone specifically analyzes data from late September or early October 2025, looking for anomalies correlated with 3I Atlas's passage, the signal might remain hidden in normal variability. GPS delays fluctuate naturally. Ionospheric density changes with time of day season's solar activity. To detect a comet-related anomaly, you'd need to compare measurements during the comet's passage with baseline values, controlling for all other variables. You'd need statistical rigor, multiple independent observations, confirmation that the anomaly wasn't just random noise. Has anyone done this analysis? I don't know. It's possible. It's also possible the data exists but hasn't been examined with this hypothesis in mind. Now consider Mars. On October 3rd, the 3I Atlas passed within 0.19 AU of the red planet. That's much closer than Earth, about 28 million kilometers. Mars has a thin atmosphere, but it does have an ionosphere. And Mars has orbiters equipped with instruments that can detect atmospheric disturbances. Mars's ionosphere is different from Earth's. Mars lacks a global magnetic field, so its atmosphere interacts directly with solar wind. Charged particles from the sun can penetrate deep into the Martian atmosphere, creating auroras that occur globally rather than just near poles, as on Earth. Could 3I Atlas's coma have interacted with Mars's ionosphere during the October 3rd close approach? Could orbiters have detected transient ionization spikes, auroral glows, or other atmospheric effects? Again, this requires someone to look. The Mars Express orbiter and the ExoMars Trace Gas orbiter both observed the comet around its closest approach. ESA announced this publicly, but what did they find? Were there atmospheric anomalies? Were there unexpected particle detections? Those results might not be published yet. Scientific analysis takes time. Data must be processed, calibrated, interpreted. Papers must be written and peer-reviewed. Months or even years can pass between observation and publication. So it's possible that Mars orbiters detected something unusual and we simply don't know about it yet because the researchers are still analyzing the data and preparing their findings. This is the atmospheric anomaly scenario. Not dramatic, not definitive, just the possibility that subtle effects occurred, were recorded by instruments, and are waiting to be recognized. If such effects exist and are confirmed, what would they mean? They'd suggest that interstellar objects can influence planetary environments in ways we haven't fully characterized. They'd show that even distant passages can have measurable consequences, and they'd raise questions about whether other interstellar visitors left similar traces that we didn't detect because we weren't looking. Now let's shift to disclosure cascades. The term disclosure carries conspiratorial connotations. It suggests hidden information, government cover-ups, secret meetings where officials decide what the public can know. And certainly such scenarios occur in fiction far more often than reality. But there's a more mundane, more plausible version of disclosure that doesn't require conspiracy. It's simply the coordinated release of information in ways that manage public perception and scientific interpretation. The International Asteroid Warning Network coordinated an observing campaign for 3I Atlas. This is public knowledge. The campaign aimed to improve astrometric measurements of comets, which present unique challenges due to their fuzzy appearance and morphological features. Multiple observatories participated. Data was shared. This is normal scientific collaboration, but consider what else might happen during such a campaign. Researchers compare observations from different instruments. They notice discrepancies, small differences that fall within error margins but seem correlated. They revisit archival data from other missions to see if similar patterns exist, and perhaps they find something. Not proof of anything extraordinary, just oddities. Timing offsets in spacecraft telemetry, slight deviations in trajectory predictions. Subtle anomalies that individually mean nothing but collectively form a pattern. What happens next? Quiet meetings. Working groups form to investigate whether the anomalies are systematic errors, calibration issues, or something real. Internal reports are written. Preliminary findings are shared among trusted colleagues. And maybe, as part of this process, certain data sets get re-released with updated calibrations. Old observations get reprocessed with new algorithms. Results that were previously buried in technical reports get highlighted in new contexts. To the outside observer, this looks like normal scientific progress. Improved measurements, refined understanding, nothing conspiratorial. But if you're paying very close attention, if you're watching the timing of publications and data releases, you might notice a pattern. A cascade of small revelations, each one building on the previous, each one slightly expanding what's considered possible. This is what a modern disclosure might look like. Not a press conference announcing alien contact, but a slow drip of information. A gradual shift in what's acknowledged as real, a process so incremental that no single moment stands out as the disclosure. And by the time the pattern becomes clear, by the time someone connects all the pieces, the moment of revelation has already passed. It wasn't a moment, it was a process, and processes are invisible until they're complete. Is this happening with 3I Atlas? There's no evidence of it. The observing campaign is explained by legitimate scientific goals. The coordination is normal for interesting objects. No unusual data releases have been flagged, but the scenario remains possible. If there were subtle anomalies in the data, if researchers noticed something that warranted closer examination, we wouldn't necessarily hear about it immediately. We'd only learn about it when papers are published, which could be months or years from now. And if those papers reveal unexpected findings, if they show that 3I Atlas perturbed something, or emitted something, or interacted with something in a way that challenges existing models, then looking back we might recognize a cascade. We might see that information was released gradually, carefully, in a way that prepared the scientific community and the public for increasingly surprising revelations. The verdict: atmospheric anomalies are possible and require analysis of existing ionospheric and spacecraft data. Disclosure cascades are plausible as a framework for understanding how surprising findings might emerge gradually rather than dramatically. Neither scenario has confirmed evidence currently, but both remain testable hypotheses that future data might support or refute. These are scenarios of subtlety, of whispers rather than shouts, of patterns that only emerge when you know to look for them. And they remind us that black swan events don't always announce themselves with fanfare. Sometimes they arrive quietly, hidden in data we've already collected, waiting for someone to ask the right question. Now we enter the strangest territory. The scenarios that have less to do with physics and more to do with perception, with consciousness, with the way human belief shapes reality. These aren't predictions about what 3I Atlas is. They're observations about what we might make of it and how that making might have consequences as real as any gravitational perturbation. Let's start with psychological singularity. History is full of moments when public attention exceeded public understanding, when collective belief created consequences independent of the facts. When Halley's Comet appeared in 1910, newspapers published stories about Earth passing through the comet's tail. Astronomers assured the public there was no danger. The tail is so diffuse, so insubstantial, that passing through it posed zero threat. But fear spread anyway. Entrepreneurs sold comet pills to protect against poisonous gases. Some people sealed their homes. There were reports of panic, of suicide, of irrational behaviors driven by anxiety rather than evidence. The comet itself was harmless, but the belief in danger created real consequences. People made decisions based on fear. Resources were wasted. Society was disrupted not by the comet's physical effects, but by psychological ones. Or consider the year 2000 bug, Y2K. Computers used two-digit year codes. Programmers warned that systems might fail when the date rolled over from 99 to 0. Billions were spent on fixes, updates, contingency plans. People stockpiled supplies. Some prepared for societal collapse. When midnight came, the transition was largely smooth. Most systems worked fine, partly because of the preparation, partly because the threat was overstated. But the preparation itself, the fear, the spending, the behavioral changes, those were real. They had economic impact, social impact, regardless of whether the underlying technical threat justified them. These are examples of psychological singularities, moments when collective belief generates its own reality. Now apply this to 3I Atlas. Speculation has been growing since discovery. Media coverage has expanded from scientific journals to mainstream outlets. Social media discussions range from informed analysis to wild conspiracy theories. And with each iteration, with each article and video and post, the object becomes more culturally significant. What if that significance crosses a threshold? What if enough people start believing something is about to happen? Not based on evidence, but based on narrative momentum, on the feeling that this time is different, on the psychological need for meaning in a universe that often seems random. Imagine social media erupts with theories. Hashtags trend. Some people report dreams about the comet. Others notice synchronicities, meaningful coincidences that seem too perfect to be chance. The number 3 appears repeatedly. October 29th aligns with historical events. Patterns emerge from noise because human brains are pattern recognition machines, and we see connections whether they exist or not. Then mainstream media picks up on the speculation, not endorsing it, but covering it. Why are people so fascinated by 3I Atlas? Experts debunk comet conspiracy theories. But by covering the speculation, by giving it attention, the media amplifies it. The theories spread further, and then policymakers start getting questions. Congressional staffers field calls from concerned constituents. Journalists ask space agencies for statements. NASA issues reassurances. The comet poses no threat. Its passage is well understood. There's no evidence of anything unusual. But those reassurances are carefully hedged. They say no evidence rather than absolutely impossible. And that linguistic caution gets interpreted as doubt, as hidden knowledge, as confirmation that something is being withheld. Suddenly the object is politically significant. Emergency management offices review protocols. Space agencies hold extra briefings. Telescope time gets reallocated to monitor the comet more closely, not because scientists think something will happen, but because the public attention demands response. And in responding, institutions make the object objectively significant. Resources flow toward it. Careers pivot around it. It becomes a central reference point for planetary defense discussions, for SETI considerations, for debates about scientific communication. The object hasn't done anything extraordinary, but belief has created consequences. The narrative has become self-fulfilling. 3I Atlas is important not because of what it is, but because of what we think it might be. This is psychological singularity, the moment when perception creates reality, when belief drives action, when the map becomes the territory, and the most unsettling aspect. There's no way to prevent it. Trying to calm fears requires communication, but communication feeds the narrative. Silence is interpreted as cover-up. Transparency is interpreted as confirmation. Every response reinforces the cycle. This scenario doesn't require Three-Eye Atlas to be unusual. It only requires us to believe it's unusual. And belief, once it reaches critical mass, is self-sustaining. Now let's move to the final, most speculative scenario: reality glitch. Modern science depends on measurement. We observe, we quantify, we compare, and underlying all measurement is time. Precise timing. Telescopes timestamp observations. Spacecraft send signals, time-stamped by onboard clocks. Pulsars serve as cosmic clocks, their regular pulses marking intervals with extraordinary precision. All of this assumes that time flows uniformly, that clocks tick at predictable rates, that the universe operates on a consistent timeline. But what if there are glitches, moments when timing systems desynchronize, when multiple independent clocks show minute discrepancies, when the fabric of measurement itself reveals inconsistencies? Imagine multiple independent observations from October 2025 show timing anomalies. Pulsar timing arrays detect residuals, deviations from expected pulse arrival times. Atomic clocks at different locations show microsecond-scale drift. Spacecraft telemetry from Mars orbiters arrives slightly earlier or later than predicted. Individually, each anomaly falls within error margins. Noise, calibration, uncertainty. Nothing significant, but suppose they all occur during the same window, the week of perihelion, the week when Three-Eye Atlas was closest to the Sun. Is that coincidence or correlation? There's no obvious mechanism for a comet to affect timekeeping on Earth. Its mass is too small to cause measurable gravitational time dilation. Its electromagnetic environment is insignificant compared to the Sun's. Standard physics says there should be no connection, but suppose the anomalies are real and correlated. What would that mean? One possibility: ionized plasma from the comet's coma affected signal propagation. Radio waves carrying timing information passed through regions of enhanced ionization, causing delays that weren't properly accounted for. This is a natural, well-understood effect. GPS systems correct for it, but in unusual conditions, corrections might be imperfect. Another possibility: instrumentation error. Multiple systems using similar calibration techniques all had the same systematic bias during the same period. This happens. Scientific instruments are complex and errors can propagate across datasets. But there's a third possibility, vanishingly unlikely but conceptually profound. The timing anomalies reveal something about the nature of time itself. Something about how measurement works, or how space-time fabric responds to certain conditions, or how our synchronization systems impose uniformity on something that isn't actually uniform. This ventures into metaphysics. It's not a hypothesis most physicists would entertain seriously, but it's worth articulating because if timing anomalies did exist and resist conventional explanation, we'd be forced to consider whether our foundational assumptions are correct. Do atomic clocks measure time, or do they measure something else that we've interpreted as time? Is the universe really synchronized across vast distances, or is synchronization an artifact of our measurement framework? These are questions that emerge only when you encounter anomalies you can't explain, and they're questions that most scientists would dismiss as philosophical rather than physical. But occasionally, very occasionally, physics forces philosophy. Quantum mechanics did this. Relativity did this. And perhaps someday an astronomical observation will do this. For Three-Eye Atlas, the reality glitch scenario is almost certainly not relevant. No widespread timing anomalies have been reported. No challenges to fundamental physics have emerged from its passage. But the scenario remains instructive. It reminds us that science operates on assumptions, and those assumptions are testable. It asks us to consider what evidence would challenge our most basic beliefs about measurement, about time, about the architecture of physical law. And it suggests that if we ever do encounter something genuinely inexplicable, something that breaks not just our models but our frameworks for building models, it might not look like a dramatic discovery. It might look like subtle inconsistencies in data, microsecond offsets that shouldn't correlate but do, timing residuals that persist across independent systems. The verdict: psychological singularity is plausible and possibly already occurring at low levels through media coverage and public interest. Reality glitch is highly speculative, unsupported by evidence, but valuable as a thought experiment about the limits of measurement and the foundations of physical law. These scenarios push boundaries. They ask uncomfortable questions, and they remind us that black swan events don't always originate in the external world. Sometimes they originate in perception, in belief in the collective human response to mystery, and sometimes they reveal that reality itself might be stranger than our instruments can capture. Let's step back. Let's zoom out from the specific details of 3i Atlas and ask a broader question: why does any of this matter? Why should we care about one comet, however unusual, passing through our solar system for a few months before disappearing forever? The answer lies in what this object represents. Not just chemically or physically, but statistically, conceptually. It's a sample, a single data point drawn from a population we're only beginning to characterize: interstellar objects. For all of human history, we've studied objects from one star system, ours. We've observed our sun, our planets, our asteroids, our comets. We've built theories about how planetary systems form, how accretion works, what chemical processes occur in protoplanetary disks, and those theories are good. They explain our solar system reasonably well, but they're built on a sample size of one stellar environment, one set of initial conditions, one particular trajectory through billions of years of evolution. Now, for the first time, we're sampling other systems. 1i Oumuamua in 2017, 2i Borisov in 2019, 3i Atlas in 2025, 3 objects, 3 different chemistries, shapes, behaviors, and each one challenges our assumptions in different ways. Oumuamua was elongated. Tumbling showed non-gravitational acceleration inconsistent with typical outgassing. Its behavior sparked debates about whether it was a comet at all or something more exotic. Avi Loeb famously suggested it might be an artificial light sail, though most astronomers favor natural explanations involving unusual outgassing or fragment geometry. 2i Borisov was more conventional. It looked like a comet, behaved like a comet, had chemistry similar to solar system comets. It was reassuring. It suggested that our understanding generalizes reasonably well beyond our local neighborhood. And then 3i Atlas arrived. Carbon dioxide rich, early activity, acceleration anomalies, chemistry that's natural but extreme, behavior that's explainable but surprising. 3 objects, 3 different stories. And the lesson is clear. Interstellar objects are diverse. They come from different formation environments, different stellar metallicities, different regions of their parent disks, different epochs of galactic history. If we've learned anything from exoplanet discoveries over the past 30 years, it's that planetary systems are wildly varied. Hot Jupiters orbit closer to their stars than Mercury does to the Sun. Super-Earths exist in configurations we never predicted. Binary systems, elliptical orbits, retrograde planets every year brings new surprises that expand our sense of what's possible. Interstellar objects will do the same. Each visitor will teach us something new about the diversity of planetary formation across the galaxy. Some will be ice-rich, some rock-rich, some metal-rich. Some will be pristine, unchanged since their formation billions of years ago. Others will be processed, altered by collisions or stellar radiation or passage through molecular clouds. And statistically, if we're detecting 3 interstellar objects already with current technology, how many are we missing? Our detection systems are biased toward bright, nearby, slow-moving objects. We catch the ones that happen to pass close to Earth at the right time when they're active and visible. But most interstellar objects probably pass undetected. They're too faint, too fast, too far from our line of sight. Estimates suggest dozens, maybe hundreds of interstellar objects transit the inner solar system every year. We're seeing only the tip of the iceberg. As our detection capabilities improve, as surveys like the Vera Rubin Observatory's Legacy survey of space and time come online, imaging the entire visible sky every few nights, we'll find more. Many more. Perhaps one per month, perhaps one per week. And each one will be an opportunity. A chance to sample another star system's chemistry without traveling light years to reach it. A chance to test theories about planetary formation under different conditions. A chance to observe object classes that don't exist in our solar system, but detection is only the first step. Characterization matters more. When we find these objects, we need to observe them quickly and comprehensively. We need spectra to determine composition. We need photometry to measure brightness and activity levels. We need trajectory data to calculate orbits and non-gravitational forces. We need radio observations to check for emissions. We need everything, and we need it fast. Interstellar objects move quickly. They pass through the inner solar system in months, and they're only bright enough for detailed observation for weeks. Miss the window, and the data is lost forever. This is why 3i Atlas matters. It's a test case, a proving ground for our ability to detect, characterize, and understand these visitors before they vanish. The lessons we learn from this object will inform how we respond to the next one and the one after that. Are we asking the right questions? Are we using the right instruments? Are we analyzing data with appropriate rigor and appropriate openness to surprise? Are we prepared to recognize anomalies and investigate them seriously? Or are we still approaching these objects with assumptions built from our single-system sample filtering data through models that might not apply, dismissing outliers as errors when they might be discoveries? The future of interstellar object science depends on how we handle these early cases.
If we're rigorous, curious, and humble, we'll build a rich data set that transforms our understanding of galactic planetary systems. If we're dismissive, incurious, or overconfident, we'll miss opportunities that won't recur. Because here's the thing, 3i Atlas will fade. It's already receding. Every day it gets dimmer, harder to observe. Within weeks it will be too faint for most telescopes. Within months it will be beyond detection entirely. And then it's gone forever. We have one chance with each object, one window of observation, and what we choose to measure, what we choose to investigate, what we choose to question or accept, those choices have lasting consequences. So yes, 3i Atlas matters, not because it's necessarily revolutionary on its own, but because it's the third step in a journey we've just begun. A journey toward understanding the diversity of matter chemistry and structure across the galaxy.
And because each step teaches us not just about the cosmos, but about ourselves, about how we respond to anomaly, how we balance skepticism and curiosity, how we prepare for surprises we can't predict. The next interstellar object is already on its way. It might be detected tomorrow or next year or a decade from now. And when it arrives, we'll have a choice approach it with the lessons learned from Oumuamua, Borisov, and Atlas, or repeat the same uncertainties, the same debates, the same missed opportunities. The universe is vast, the universe is diverse, and it's sending us samples. The question is whether we're ready to read the messages they carry. While we've been focusing on 3i Atlas, I want to pull your attention to something else happening in the cosmos, something that might, in a strange and indirect way, be connected to the story of interstellar visitors. It's a phenomenon that's been puzzling astronomers for 2 decades, generating more questions than answers. Fast radio bursts, FRBs. These are brief pulses of radio energy lasting just milliseconds that arrive from random directions in the sky with extraordinary intensity. The first one was discovered in 2001, buried in archival data from the Parkes telescope in Australia, though it wasn't recognized as significant until years later. Since then, we've detected hundreds, maybe thousands, depending on how you categorize them. Most FRBs are one-offs. They flash once and never repeat, making them nearly impossible to study in detail. You detect the burst, you record its properties, and then nothing. It's gone. The source has vanished, or moved on, or exhausted whatever process created the emission, but some FRBs do repeat, and the repeating ones are especially mysterious because repetition implies a persistent source. Not a catastrophic explosion, not a single collision or merger, but something that can fire multiple times. Something with a mechanism that survives and reactivates. The leading hypothesis is magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These fields can stress the crust, causing fractures that release enormous energy bursts. Or they can create conditions for coherent radio emission through processes we don't fully understand. Magnetar models explain some FRB properties, but struggle with others. Here's what makes FRBs relevant to our discussion: they're anomalies that challenged our assumptions. When first detected, they didn't fit any known astrophysical process. They were too bright, too brief, too structured to be natural. Some researchers even speculated about artificial origins, perhaps signals from extraterrestrial civilizations with enormously powerful transmitters. That speculation was quickly dismissed by most astronomers. And as observations accumulated, natural explanations became more compelling. But the point is, FRBs expanded the space of what we know is possible. They revealed a class of phenomena that theory hadn't predicted. Now consider this. What if there are other FRB-like phenomena we haven't detected? What if there's a spectrum of radio transients ranging from extragalactic bursts that travel billions of light years, down to local emissions that occur within our solar system or just beyond? We've optimized our detection systems for strong, distant bursts. But what about weak, nearby ones? What about emissions that don't fit the template we're searching for? Here's where it connects to 3i Atlas. Radio telescopes don't routinely observe comets looking for emissions. We don't expect comets to generate coherent radio waves. They're passive objects that reflect and scatter electromagnetic radiation but don't produce it. But what if under specific conditions, a comet's ionized coma can generate radio emission? What if interactions between the coma's plasma and the solar wind create instabilities that produce brief structured pulses? This is speculative. Plasma physics is complex, nonlinear, full of phenomena that can produce unexpected effects. Magnetic reconnection events, for instance, can release energy suddenly generating radio emission. Could this happen in a comet's coma? I don't know, but it's not obviously impossible. And if it can happen, if comets occasionally emit weak radio pulses, we wouldn't know because we're not looking. Or, in the more provocative interpretation, what if an FRB detected in October 2025 came from the vicinity of 3i Atlas? Not from the comet itself as a natural object, but from something associated with it. A brief transmission deliberately timed, deliberately structured. This is wild speculation. But here's why it's worth considering. Radio all-sky monitors like CHIME continuously scan large patches of sky. They detect FRBs regularly. If an FRB occurred near 3i Atlas's position during perihelion, it would show up in the data. Has anyone checked? Has anyone correlated FRB detections from October 2025 with the comet's sky coordinates? Maybe someone has, maybe they found nothing, or maybe they found something ambiguous, a weak emission that could be a distant FRB seen through a fortuitous alignment, or could be something closer, something local, something that demands a different explanation. The challenge with correlations is that they're easy to find if you're looking for them, and easy to miss if you're not. If you don't hypothesize a connection between comets and radio bursts, you don't search for coincident events. And if you don't search, you don't find. This is the pattern recognition problem at the heart of modern astronomy. We generate more data than we can analyze. We build pipelines that filter and categorize automatically, and those pipelines embody assumptions about what's interesting and what's noise. Machine learning could help. Neural networks can identify patterns without being told what to look for. They can scan datasets for anomalies, for correlations, for structures that human-designed algorithms miss. But even machine learning requires someone to ask the question. Someone has to decide to train a network on radio transient data and comet positions. Someone has to say, let's see if there's a connection. And that requires a mindset that treats even unlikely hypotheses as worth investigating, not because you expect them to be true, but because the cost of missing something extraordinary is higher than the cost of checking and finding nothing. So here's my suggestion. Someone should do this analysis. Correlate FRB detections from 2025 with positions of known solar system objects, especially interstellar visitors. Check for coincidences. Apply statistical rigor to determine whether any correlations are significant or just chance alignments. If nothing turns up, fine. We've ruled out a hypothesis. If something does turn up, if there's even a weak correlation that survives statistical testing, then we have a new mystery to investigate. Because the universe has shown us repeatedly that it's more diverse, more surprising, more rich with phenomena than our theories capture. Fast radio bursts reminded us of this. Interstellar objects are reminding us again, and perhaps, just perhaps, these two mysteries are connected in ways we haven't imagined yet. Let me tell you about a revolution that's happening quietly in astronomy. Not telescopes getting bigger, not spacecraft reaching farther. Something different, something that might change how we discover entirely. Artificial intelligence is learning to see what we cannot. For decades, astronomy has been limited by human perception and human analysis. We build instruments that collect data. We design algorithms that process it. We examine images, spectra, light curves. We look for patterns that match our theories, for anomalies that violate our expectations. But we can only find what we're looking for. If a phenomenon doesn't fit our mental categories, if it doesn't match the templates we've programmed into our detection software, it gets classified as error or noise. It gets filtered out, archived, forgotten. This is not a failure of intellect. It's a limitation of bandwidth. The volume of data is staggering. The Vera Rubin Observatory, when it begins, operations will generate 20 terabytes of imaging data every night. Every night. No team of humans can examine all of it. No traditional algorithm can process every image looking for every possible anomaly. So we prioritize. We optimize for specific categories: supernovae, variable stars, asteroids, transients. We build pipelines that flag those objects and discard everything else. And everything else might contain discoveries we'd never think to search for. Enter machine learning. Neural networks that can be trained on massive data sets, learning to recognize patterns without being explicitly programmed with rules. These systems don't know what they're looking for. They just learn what different looks like, and they're making discoveries. In 2023, researchers applied deep learning to old Kepler Space Telescope data. Kepler had already found thousands of exoplanets using traditional detection algorithms. Those algorithms looked for periodic dips in starlight caused by planets transiting across their star's disk, regular, predictable, clear signals. But the neural network found more. Planets the original pipeline missed. Planets with irregular orbits, with transits perturbed by neighboring worlds, with signatures too subtle or too complex for rules-based detection. The data was there all along, in archives, publicly available. But it took a different kind of analysis to reveal patterns the human-designed algorithms had filtered as noise. The same thing is happening in other fields: galaxy morphology, variable stars, gravitational lenses. AI systems are finding examples that don't fit standard categories, that represent transitional states or rare configurations human classifiers overlooked. And here's the crucial insight. These systems aren't replacing human astronomers. They're showing us where to look. They're flagging anomalies saying, hey, this is weird. You should examine this more closely. Now imagine applying this to 3i Atlas. Imagine feeding every available observation into a neural network. Every light curve showing how brightness changed over time. Every spectrum showing absorption and emission lines. Every trajectory measurement. Every polarimetric profile, every image from every telescope that observed the comet from July through October. You don't tell the network what a normal comet looks like. You don't program it with expectations about outgassing or acceleration or chemistry. You just feed it data and ask what patterns exist here, what correlations, what anomalies. Maybe the network finds periodic brightness variations with a 6.3-hour cycle that's too regular for random outgassing but too erratic for simple rotation. Maybe it detects subtle color changes in the coma that correlate with distance from the sun in unexpected ways. Maybe it identifies structures in high-resolution images that suggest directed jets or asymmetric emission. None of this would be proof of anything artificial or extraordinary, but it would be interesting. It would be worthy of investigation. It would guide where to point telescopes, what wavelengths to observe, what models to test. This is the future of discovery. Human intuition plus machine perception. We provide the questions and the interpretations. AI provides the pattern recognition that operates at scales and sensitivities beyond human capability. But there's a challenge. AI has one fatal flaw: it doesn't understand. It can't distinguish between signal and noise, between meaningful pattern and random coincidence, between discovery and artifact. That's where we come in. Humans verify. We replicate. We test whether patterns persist across independent data sets, across different instruments, across different analysis methods. We apply physical reasoning, asking whether a pattern makes sense or violates fundamental laws. And we decide what constitutes sufficient evidence. AI can flag 1 billion anomalies. We have to determine which ones matter. So, has anyone done this for 3i Atlas? Has anyone applied state-of-the-art machine learning to the full dataset? Publicly, I haven't seen reports. But that doesn't mean it hasn't happened. Maybe a graduate student somewhere is running TensorFlow on a GPU cluster training networks on comet data. Maybe a national lab has internal projects exploring AI-driven analysis of solar system objects. Maybe the analysis is happening right now and results haven't been published yet because researchers are still validating what they've found. Or maybe, and this is the frustrating possibility, maybe no one has tried. Maybe our greatest cosmic anomaly is slipping through our fingers because no one thought to unleash the full power of modern AI on it. If that's true, it's a missed opportunity of historic scale, because if 3i Atlas has something unusual in its data, something that humans overlooked but machines could detect, we have a limited time to find it. The comet is fading. Additional observations become harder each day. Eventually, the observation window closes and we're left with whatever data we collected. If an AI finding emerges years from now, if someone in 2028 reanalyzes archived 2025 data and discovers a pattern, we won't be able to follow up. The object will be too distant, too dim. We'll have tantalizing hints and no way to confirm them. This is the urgency. This is why advanced analysis methods should be applied now, not later, because later might be too late. The revolution in AI-driven astronomy is coming. It's already here in many fields. The question is whether it arrives in time for 3i Atlas or whether this object becomes a cautionary tale, a visitor we studied but didn't fully understand because we didn't use every tool available.
And if we miss something in this object, what will we miss in the next? How many discoveries lie buried in data waiting for algorithms that don't exist yet, for questions no one thought to ask? The universe is sending us messages. The question is whether we're prepared to decode them. Not with our eyes and our theories alone, but with every tool at our disposal.
human and artificial intuitive, and algorithmic skeptical and curious. Because somewhere in the terabytes of observations we've collected in the millions of pixels and photons and spectral lines, there might be a signal, a pattern, a truth we haven't recognized yet, and if there is, the machines will find it. The question is, will we be listening? When they do, right now as you hear these words, Space Atlas is moving away from the sun. It's receding, fading. Every hour it gets a little dimmer, a little harder to observe. The window, that brief period when it's bright enough for detailed study, is closing. This is the nature of transient astronomy. Objects appear, they're visible for a limited time, and then they're gone. Supernovae fade over weeks. Variable stars cycle through brightness changes. Asteroids pass by and disappear into the vastness of space. For interstellar visitors, the window is especially narrow. They move fast. 3i Atlas is traveling at 61 kilometers per second. They don't return. They're not in closed orbits around the sun. They're on hyperbolic trajectories, one-way journeys through our solar system and back out into interstellar space. We get one chance, one opportunity to observe, measure, characterize. And that opportunity has a countdown attached to it. So what observations still matter? What measurements are critical before the object becomes too faint? First, brightness evolution. How is the light curve changing? Post-perihelion, is the comet decaying in brightness as expected, following the power law relationship with distance from the sun? Or is there a secondary peak suggesting delayed outgassing or fragmentation? Photometry is relatively easy. Small telescopes can track brightness, but someone needs to be watching continuously, collecting data points every night if possible. Any deviation from expected behavior could be significant. Second, non-gravitational acceleration. Is the comet's trajectory continuing to match predictions? Or are there deviations, small changes in position that can't be explained by gravity alone? This requires precise astrometry, measuring the comet's position against background stars with high accuracy. It's challenging as the object fades because position measurements become less precise. But it's crucial because trajectory anomalies could reveal ongoing outgassing fragmentation events, or in the most speculative scenario, course corrections. Third, radio telescope follow-up. Has anyone systematically scanned 3i Atlas at radio wavelengths, looking for emissions? Not just during perihelion, but afterward. Radio emission doesn't depend on reflected sunlight. If the comet is generating radio waves through plasma processes, or if there's an embedded transmitter, it might remain detectable even as optical brightness fades. This requires telescope time at facilities like the Green Bank Telescope Arecibo. Wait, no, Arecibo collapsed in 2020. The Very Large Array, FAST in China. These instruments could potentially detect weak radio signals from a comet-sized object within a few astronomical units. Has this been done? I don't know. Radio astronomy of comets is uncommon. It might not have been prioritized, but it should be. Fourth, spectroscopic follow-up. How is the comet's composition evolving? Is the carbon dioxide to water ratio changing as the comet moves farther from the sun? Are new molecular species appearing or disappearing? Spectroscopy requires larger telescopes and longer integration times as the object fades, but it's essential for understanding the outgassing processes. If the chemistry changes in unexpected ways, that tells us something about the internal structure, about layering in the nucleus, about temperature gradients and sublimation fronts. Fifth, fragmentation monitoring. High-resolution imaging to check whether the nucleus has broken apart. The Hubble Space Telescope, the James Webb Space Telescope, ground-based adaptive optic systems, any instrument capable of resolving structure at the comet's distance. If fragmentation occurred, we'd see multiple components in images. Their separation would increase over time. And if any fragment showed anomalous motion, that would be immediately apparent from tracking their relative positions. Sixth, and perhaps most importantly, archival work. The observations have been made, months of data exist, but has all of it been analyzed? Have researchers looked for correlations between outgassing and acceleration? Have they checked radio archives for coincident transients? Have they examined ionospheric data for anomalies during close approaches to Earth and Mars? This work doesn't require the comet to still be visible. It requires time, computational resources, and willingness to investigate hypotheses that might seem unlikely. But unlikely isn't impossible. And checking costs relatively little compared to the potential value of finding something unexpected. Here's what makes this moment critical. Once the comet fades below detection thresholds, the data becomes fixed. We won't get new observations. The archive is complete. And whatever we didn't measure, whatever we didn't think to look for, remains unknowable. This happens all the time in astronomy. Objects are observed, data is collected, and years later someone asks a question that requires information we didn't capture. If only we'd taken a spectrum at that wavelength. If only we'd measured polarization. If only we'd pointed a radio telescope. The object is gone. The opportunity is lost. And we're left with regret. So for 3i Atlas, this is the moment. This is when we decide what legacy this object leaves. Will it be fully characterized, observed across every wavelength, analyzed with every technique? Or will it be partially documented with gaps in coverage, with questions unanswered because we didn't think they were important at the time? The astronomers observing right now, professionals and amateurs with large instruments and small, are creating the permanent record. The measurements they make in October, November. December 2025 will be the definitive data set. Everything we learn about 3i Atlas in the future will be based on what they capture now. And 20 years from now, when we've observed dozens more interstellar objects, when we've built better theories and more sophisticated models, researchers will return to the 3i Atlas data and ask new questions. Questions we haven't thought of yet. Questions about patterns that only emerge when you compare multiple objects. Will the data be sufficient to answer those questions? Will we have measured the right things? Or will 3i Atlas be the object that taught us what to look for, what to measure, what not to miss with the next visitor? Either outcome is valuable. Either way we learn, but there's a difference between learning from complete data and learning from missed opportunities. The window is closing. Every night the comet fades a little more. And every night we don't observe is a night of data we'll never recover. Someone somewhere is looking. Telescope domes are opening. Instruments are pointing. Data is flowing into hard drives and archives. But is it enough? Are we watching closely enough, measuring thoroughly enough, asking the right questions? Because 3i Atlas won't wait. It's not lingering for our convenience. It's following the trajectory gravity carved billions of years ago. And that trajectory leads away from the sun, away from Earth, away from our instruments and our curiosity. Soon it will be too faint. Soon it will be gone. And all we'll have are the memories and the data, the images, the spectra, the measurements, and the questions we didn't answer because we ran out of time. The universe offers glimpses, not reruns. When an interstellar visitor passes through, we get one showing, one chance, and the credits are about to roll on 3i Atlas. Are we still watching, or have we already looked away? After all this exploration, all these scenarios and hypotheses and questions, let's step back and assess. What do we actually know? What remains uncertain? And what does 3i Atlas teach us about how we respond to cosmic anomalies? Let me summarize the 8 scenarios we examined, evaluating each for plausibility, potential impact, and current evidence. Scenario 1. Orbital domino. Plausibility medium. Gravitational perturbations, our real orbital mechanics, are chaotic over long timescales, and 3i Atlas passed close enough to Mars to potentially influence nearby objects. Potential impact. High. A cascade effect could create future collision risks decades from now. Evidence none yet, but this is expected. The timescales are too long. We won't know for years or decades whether anything was perturbed significantly. Scenario 2, fragmentation event. Plausibility medium.
Comets fragment regularly, and perihelion thermal stress makes this likely. An anomalous fragment showing directed motion is less likely but not impossible. Potential impact. Medium to high depending on the fragment's behavior. Evidence. No confirmed fragmentation as of perihelion, but this could occur in the weeks following. Continued monitoring is critical. Scenario 3. Solar disruption. Plausibility low. No known mechanism exists for a comet to trigger solar activity, and no major solar events coincided with perihelion. Potential impact. High if it occurred. Infrastructure disruption raised questions about unknown physics. Evidence none. The scenario loses credibility for this specific object. Scenario 4. Artificial signal. Plausibility very low. Requires extraordinary assumptions and lacks supporting evidence. Potential impact. Extreme would confirm extraterrestrial technology and transform human understanding. Evidence none publicly acknowledged.
Archival searches might reveal ambiguous data, but nothing definitive has been reported. Scenario 5. Atmospheric anomaly. Plausibility low to medium. Depends on whether the comet's coma intersected Earth's or Mars's magnetosphere in detectable ways. Potential impact low to medium would suggest unexpected particle interactions. Evidence unknown. Requires analysis of ionospheric monitoring data and Mars orbiter logs from October 2025. Scenario 6. Disclosure cascade. Plausibility low to medium. Coordination is normal scientific practice, but identifying intentional information management is difficult. Potential impact. Medium would affect public trust and suggest prior detections were not announced. Evidence circumstantial at best. The IAWN campaign is public and explained by legitimate scientific goals. Scenario 7. Psychological singularity. Plausibility. Medium. Social dynamics are unpredictable, and belief-driven consequences are historical fact.
Potential impact. Medium real policy shifts. Funding changes social responses based on perception rather than data. Evidence observable in media coverage and public interest, already occurring at low levels. Scenario 8. Reality glitch. Plausibility very low. Requires unknown physics or systematic instrumentation error. Potential impact. Extreme would challenge fundamental assumptions about timekeeping and space-time. Evidence none. Would require extensive archival analysis across multiple independent timing systems. So what does this assessment tell us? Most scenarios are low probability. A few have plausible mechanisms but lack confirming evidence. One or two might already be manifesting subtly, and none currently meets the criteria for a full black swan event, though orbital domino and fragmentation remain possible over longer timescales.
But here's the deeper question. If 3I Atlas is scientifically normal, if it's explainable within existing models, why is it still generating so much discussion? Why are we entertaining exotic hypotheses at all? The answer is that normal is more complicated than it appears. Yes, we can propose natural explanations for every anomaly. Unusual composition could have formed in a carbon-rich region. Early activity carbon dioxide sublimates easily. Acceleration discrepancy, dense nucleus or symmetric jets. Extreme polarization, unusual dust properties. Each explanation is plausible. Each is consistent with physics. But collectively, they require 3I Atlas to be exceptional in multiple ways simultaneously. It's not just unusual in one aspect, it's unusual in many aspects. And statistically, finding an object that's an outlier in multiple independent parameters is, well, unlikely. Not impossible. Outliers exist. But when multiple rare properties coincide in one object, it makes you wonder whether there's an underlying cause connecting them.
Maybe that cause is simply the object's interstellar origin. Maybe conditions in another star system produce naturally comet-like objects that differ systematically from ours. Maybe we're seeing normal variation expanded across galactic scales. Or maybe we're missing something. Maybe our models are incomplete in ways we haven't recognized. Maybe there are formation mechanisms, interaction processes, material properties that we haven't encountered yet because we've only studied our local neighborhood. This is why interstellar objects matter so much. They're tests. Every visitor tests whether our theories generalize beyond one star system. And 3i Atlas is showing us that generalization is harder than we thought. Which brings us to systems preparedness. Are we ready for interstellar visitors? Do we have the infrastructure, the protocols, the scientific frameworks to study them effectively, partially? Planetary defense networks track near-Earth asteroids excellently. We have sophisticated models for predicting impacts, calculating orbits, planning deflection missions. But these systems aren't optimized for interstellar objects that move faster, arrive from unexpected directions, and may have properties we haven't characterized. SETI searches for signals, but focuses on stars and galaxies, not passing comets. Radio surveys exist, but aren't designed to correlate transients with solar system objects. Space agencies monitor solar activity, but don't systematically check for correlations with small body passages. The systems are siloed, specialized, optimized for known threat categories. So should we change this? Should we treat every interstellar visitor as a potential black swan by default? There's an argument for yes. The cost of comprehensive observation is high, but finite telescope time, instrument development personnel, hours. The cost of missing something extraordinary is potentially infinite missed scientific discoveries, undetected threats, lost opportunities for understanding. This is risk management under deep uncertainty. You can't calculate probabilities accurately when you have 3 data points. You can't build models when the parameter space is almost entirely unexplored. In such situations, the rational response is precautionary. Observe comprehensively. Analyze rigorously. Consider unlikely hypotheses seriously, not because you expect them to be true, but because the consequences of missing them are severe. And this leads to the meta-insight we might already be inside the event. Black swans aren't recognized as they occur. They're identified retrospectively. The 2008 financial crisis wasn't called a black swan while markets were collapsing. It was called a crisis, a problem, a situation requiring response. Only afterward, looking back, did it become clear that the event had characteristics of a black swan. So, if 3i Atlas is part of a black swan process, if it's quietly rewriting assumptions in ways we'll only understand years from now, we wouldn't know yet. We're too close. We're inside the event horizon of surprise. Maybe in 2030, researchers will connect orbital perturbations from 2025 to asteroid trajectories that have shifted. Maybe in 2035, AI analysis of archived data will reveal patterns we missed. Maybe in 2040, when dozens of interstellar objects have been studied, 3i Atlas will be recognized as the first example of a new category we hadn't conceived of in 2025. Or maybe it's just a comet. Weird but natural. Outlier but explicable. A curious footnote in the history of astronomy that taught us about chemical diversity in other star systems. Both outcomes are valuable. Either way, we learn. The question is whether we learn with complete data or incomplete, whether we approach the next visitor with wisdom gained from thorough study or with regrets about what we didn't measure. And that ultimately is the lesson of 3i Atlas. Not what it is, but how we respond to not knowing. Do we dismiss anomalies because they're uncomfortable? Do we overreact and see aliens in every outlier? Or do we find balance, skeptical but curious, rigorous but open, prepared for the probable while alert for the impossible? The universe is full of surprises. 3i Atlas is one. There will be more, many more. And our response to this visitor sets precedent for how we'll handle the next, and the one after that. Are we ready? That's the question we should be asking. Not, is this a black swan, but are we prepared if it is? Because preparation doesn't require certainty. It requires humility, the acknowledgement that we don't know what we don't know, and that discovery comes from looking carefully at what makes us uncertain. Squash Atlas made us uncertain, and in that uncertainty lies the possibility of growth. Let me take you forward now, not into speculation about 3i Atlas specifically, but into the larger pattern, the inevitable future that's already approaching. More interstellar objects are coming. This isn't prediction, it's certainty. They're already en route, crossing the vast distances between stars, some of them destined to pass through our solar system in months, years, or decades. Current estimates suggest dozens of interstellar objects larger than 100 meters cross the inner solar system every year. Most go undetected because they're too faint, too fast, or too far from our line of sight.
We catch only the brightest, closest, most conveniently timed visitors. But detection capabilities are improving. The Vera Rubin Observatory, once fully operational, will survey the entire visible sky every few nights with unprecedented sensitivity. It's designed to find asteroids, supernovae, variable stars, anything that changes. And interstellar objects change position rapidly, making them ideal targets. When Rubin comes online, we might detect one interstellar visitor per month. Maybe one per week. The trickle becomes a stream. And each one will be different. Each will carry chemistry from a different stellar environment. Each will have a different formation history, different composition, different structure. Some will be pristine relics, unchanged since their birth billions of years ago. Others will be processed, altered by radiation collisions, passage through molecular clouds. Some will be icy like comets. Some will be rocky like asteroids. Some might be metallic fragments of shattered planets from catastrophic collisions in other systems. And some perhaps will be objects we have no category for, things that don't fit our taxonomies because they formed under conditions we've never imagined. This is the diversity waiting for us, and it raises a fundamental question: how do we respond? Do we treat every interstellar visitor as a potential black swan worthy of comprehensive observation and extensive analysis? Or do we prioritize focusing resources on objects that seem most unusual while letting the routine visitors pass with minimal study? There's no perfect answer. Resources are limited. Telescope time is precious. Analysis requires skilled people and computational power. We can't study everything with maximum effort, but we can be strategic. We can establish protocols for initial characterization, minimum observation sets that provide basic parameters, orbit size, estimate composition, activity level. And then we can triage objects that fit expectations, get standard follow-up. Objects that show anomalies get intensive study. This requires defining expectation carefully. As we observe more interstellar objects, we'll build statistical distributions. We'll learn what typical composition ranges look like, what typical brightness profiles are, what typical acceleration signatures mean. And gradually, we'll be able to say, this one is ordinary for interstellar objects, versus this one is an outlier even among outliers. 3i Atlas might fall into the latter category. Time will tell, but the broader lesson is about mindset. We need to cultivate intellectual humility, the acknowledgement that surprises will continue, that the universe is more inventive than we are, that black swan events occur precisely because we don't expect them. This humility should inform how we build systems. Detection networks should be broad, not narrowly optimized for one type of object. Analysis pipelines should be flexible, capable of recognizing patterns they weren't explicitly programmed to find. Response protocols should include pathways for investigating unlikely hypotheses, not just reflexively dismissing them. And communication should be honest. When we don't know something, we should say so clearly. When we're uncertain, we should quantify that uncertainty. When we detect anomalies, we should present them as anomalies, interesting, worthy of study, possibly important, without immediately polarizing into "it's definitely natural" versus "it's definitely aliens." The dichotomy is false. Most things are natural. A few things might not be. And the only way to know is to look carefully and honestly without predetermined conclusions. Now let's connect everything we've discussed: orbital perturbations, fragmentation signals, atmospheric effects, AI analysis, FRBs, to the larger questions about our place in the universe. If interstellar objects are common, if dozens or hundreds pass through every year, then space is more crowded than we thought. The galaxy is a busy place filled with debris and wanderers, material exchanged between star systems on timescales of millions of years. This has implications for panspermia, the idea that life could be transported between worlds. If comets and asteroids regularly travel between stars, if they carry organic material and possibly even microorganisms, then life might be more cosmopolitan than we realize. A chemistry experiment that succeeded in one system could seed others. It also means we're surrounded by samples. We don't need to send spacecraft light years away to study other star systems. They're coming to us. Every interstellar visitor is a free sample delivered to our doorstep by the dynamics of the galaxy. This is an extraordinary gift, and we should treat it as such, but it also means we need to think about biosecurity. If interstellar objects carry material from other worlds, could they carry biological contamination? Should we be concerned about forward or backward contamination, about introducing alien chemistry into our biosphere or vice versa? These are questions for the future, not immediate threats, but they're worth considering as the stream of visitors increases. And then there's the SETI angle. If technological civilizations exist, if they've developed the capability to send probes or signals, interstellar objects would be excellent carriers. A probe embedded in a comet could hibernate for billions of years. Wake when approaching a star, gather data, transmit. This isn't science fiction. Given what we know about technology trends, about miniaturization and durability and autonomous systems, such probes are technically feasible. Whether anyone has built them is a separate question. But feasibility means we should look. And looking doesn't require believing. It requires thoroughness.
Pointing radio telescopes, checking for anomalous motion, analyzing chemistry for signatures inconsistent with natural formation, taking the possibility seriously enough to test it rigorously. If we find nothing, we've gained knowledge, we've constrained the parameter space for technological objects. If we find something, we've made the most important discovery in human history. The asymmetry argues for vigilance. So what's the long view? Where does this lead? Over the next few decades, we'll catalog hundreds or thousands of interstellar objects. We'll build statistical populations. We'll identify patterns and outliers. We'll refine theories about planetary formation, about galactic chemical evolution, about the life cycle of star systems. And maybe among those thousands, one will be undeniably extraordinary. Not just unusual, but unmistakable.
An object that defies all natural explanations, that passes every test for artificiality, that forces us to confront the reality of extraterrestrial intelligence. Or maybe not. Maybe every object will fit somewhere within natural variation, teaching us that the universe is diverse but comprehensible, surprising but not inexplicable. Either outcome advances human knowledge. Either way, we grow. But the process, the journey from observation to understanding, that's where we find meaning. That's where we discover not just facts about the cosmos, but truths about ourselves. About our curiosity, our humility, our courage to face uncertainty. 3i Atlas is one step in that journey. A strange comet, an interstellar visitor, a messenger from distant shores. It's challenged our assumptions, raised our questions, invited us to look more carefully at what we think we know, and soon it will be gone. fading into the darkness, receding beyond detection, joining the vast population of objects drifting between the stars. But the questions it raised remain, and the next visitor is already approaching, carrying its own mysteries, its own lessons. Will we be ready? That's not a question about telescopes or technology. It's a question about mindset, about whether we've learned from 3i Atlas to approach anomalies, with both skepticism and curiosity, both rigor and openness. The universe is vast, the universe is ancient, and it's full of surprises that our current theories can barely imagine. Somewhere out there, another object is falling toward the sun. It might be ordinary, it might be extraordinary. We won't know until it arrives, but we can be ready. We can watch, we can measure, we can question, and we can stay humble in the face of mystery, knowing that every answer leads to deeper questions. This is the nature of discovery, not certainty but process, not conclusions but curiosity, not knowing but seeking. And in that seeking, we find what it means to be human in a cosmos that vastly exceeds our understanding. 3i Atlas came and will soon go, but its legacy remains the reminder that we're still learning, still discovering, still capable of surprise. And that's as it should be, because a universe fully understood would be a universe fully diminished. Mystery is not our enemy. It's our invitation to look deeper, to question harder, to imagine more boldly, and to stay open to the possibility that the next discovery, the next visitor, the next glimpse into the cosmos might reveal something we never thought possible. That's the gift of interstellar objects, not answers but wonder, not certainty but awe, and the knowledge that we're part of something far larger, far stranger, far more magnificent than we've yet comprehended. The visitors will keep coming, and we'll keep watching, because that's what we do, that's who we are. Curious, persistent, humble before the infinite, and always wondering what comes next. So here we are, at the end of our journey through possibility and uncertainty. We've explored 8 scenarios that could transform 3i Atlas from curiosity into crisis. We've examined evidence, weighed probabilities, considered consequences. And what do we know? We know that 3i Atlas is a comet from another star system, that it has unusual chemistry, carbon dioxide dominant in ways we've never seen, that it became active earlier than expected, that its non-gravitational acceleration doesn't perfectly match models, that its trajectory aligned unusually with our planetary plane. We know it's challenging assumptions, pushing boundaries, operating at the edges of parameter space where our theories become less certain. But we don't know what that means. We don't know whether these anomalies cluster for a reason or simply represent natural variation from another stellar environment. We don't know whether we're missing something fundamental or simply encountering diversity we haven't sampled before. And that uncertainty is exactly where science lives. Not in the certainties we've established, but in the gaps between observation and explanation. In the space where questions grow. Some of those questions will resolve with more data, with better models, with time and analysis and the gradual accumulation of observations from more interstellar visitors. Other questions might deepen, might lead to new mysteries, new anomalies, new challenges to what we thought we understood. That's the nature of discovery. You don't get to choose what you find. You only get to choose how you look. And 3i Atlas has taught us something important about how to look. It's taught us to be vigilant without being paranoid, to be skeptical without being dismissive, to be rigorous without being closed-minded, to distinguish carefully between what we know and what we believe. These are lessons that extend beyond this one object. They apply to every anomaly we encounter, every mystery we investigate, every moment when data doesn't quite match expectations. Because black swan events don't announce themselves. They hide in noise. They masquerade as errors. They wait for someone brave enough or curious enough or lucky enough to notice that something doesn't fit. And maybe 3i Atlas is one.
Maybe it's the beginning of a cascade we won't recognize until years from now when we look back and wonder how we missed the signs. Or maybe it's just a comet. Weird but natural, outlier but explicable, a cosmic accident that happened to challenge our models in interesting ways but ultimately fits within the bounds of natural phenomena. We don't know yet. And that's okay. Not knowing is part of the process. Uncertainty is the price of discovery. What matters is that we looked, that we measured,
That we asked questions and entertained possibilities and didn't reflexively dismiss what made us uncomfortable. And now, as 3i Atlas fades from view as it recedes into the darkness from which it came, we're left with data, with measurements, with memories of a brief encounter with something from beyond, and with the knowledge that more visitors are coming, that this is not the end, but the beginning, that we're entering an era where interstellar objects will be routine, where sampling other star systems becomes part of regular astronomy. Each visitor will teach us something. Each will challenge us in different ways, and gradually, observation by observation, comet by comet, will build understanding of how planetary systems form and evolve across the galaxy. But we'll also encounter surprises. We'll find objects that don't fit, phenomena we can't explain, moments when the universe reminds us how much we don't know. And in those moments, we'll remember 3i Atlas. The strange comet that arrived in summer 2025 rounded the sun on October 29th and departed, leaving more questions than answers. We'll remember how it made us think, how it made us wonder, how it invited us to consider possibilities we dismissed, to look at data more carefully, to stay humble before the infinite. Because that's the real lesson. Not about this comet specifically, but about how we engage with mystery, with curiosity rather than fear, with openness rather than certainty, with the courage to say, I don't know, and the determination to find out. The universe is vast and strange and full of wonders we haven't imagined yet. 3i Atlas is one. There will be others, many others, and each time something arrives that challenges our understanding, we'll have a choice: dismiss it as noise or investigate it as signal, retreat to comfort or advance into uncertainty, close our minds or open them wider. The choice we make determines not just what we discover, but who we become. Science is not just a body of knowledge, it's a way of being in the world. A commitment to honesty, to evidence, to following questions wherever they lead. It's the willingness to be wrong, to revise, to grow, and it's the capacity for wonder, for awe, for humility before mystery. 3i Atlas offered us all of that. A mystery, an invitation to wonder, a reminder that we're still at the beginning of understanding. And now I leave you with one final question. Not a question I can answer. A question only you can contemplate as you look up at the night sky, as you think about that distant comet fading into darkness. If we're inside a Black Swan event right now, if 3i Atlas is quietly rewriting the rules in ways we haven't recognized, would we even know? Or would we only understand decades from now when we look back with knowledge we don't yet have? With perspective we can't yet achieve, and wonder how we missed what was always there, hiding in plain sight, waiting for us to see. The comet is leaving, but the question remains. And perhaps that question, more than any answer, is what this visitation was meant to give us. Not certainty, but wonder. Not conclusions, but curiosity. Not knowing, but seeking. And in that endless seeking, we find what it means to be human in a universe that endlessly exceeds our grasp. The sky is full of mysteries, and somewhere out there, another visitor is approaching, carrying the next chapter of a story we've only just begun to read. Will we be watching when it arrives?